We find ourselves floating in a place where the impossible becomes real, where clouds shimmer not with water vapor, but with vaporized gemstones, and where rain falls that would be recognizable on Earth, not as weather, but as treasure. Floating high in the atmosphere of a world called HAT-P-7b, suspended where the temperature allows aluminum oxide to condense from gas into tiny crystals. We are surrounded by something no human eyes have witnessed directly, but which science confirms exists 1,000 light years from home. The clouds around us glow with metallic brilliance, catching starlight from the nearby sun and reflecting it in shades of blue and red, colors created not by water droplets scattering light, but by the fundamental nature of corundum itself, the mineral that forms rubies and sapphires on Earth when found in solid rock. This is where we begin our journey, among clouds made of gemstones, in an atmosphere so hot it turns solid minerals into vapor that condenses and falls as crystalline rain. The color strikes us first, a deep blue shimmer that catches the starlight filtering through these metallic clouds, creating reflections and refractions that make the atmosphere appear almost liquid. The clouds stretch in layers above and below our floating vantage point, forming deck upon deck of shimmering mineral haze, extending for hundreds of kilometers in every direction. The blue comes from trace amounts of iron and titanium mixed into the aluminum oxide structure, the same impurities that give sapphires their characteristic color in terrestrial gemstones. Some regions show hints of red instead, ruby tones emerging where chromium dominates the crystal structure, creating the crimson hues we associate with the most precious of gems. These metallic particles drift through an atmosphere far denser than the air we breathe at home. You are listening to the Drowsy Astronaut, where we take our time exploring the cosmos in ways that allow both learning and rest to happen naturally. Tonight, we visit a single world in depth, HAT-P-7b. From the gemstone rain in its clouds, to the star it orbits, to the story of how we discovered such an impossible place. If you are settling in, wherever you find yourself tonight, perhaps leave a comment about what draws you to these explorations of distant worlds. We explore one world tonight, deeply and completely, beginning here, among clouds made of gemstones. The clouds themselves exist at a specific altitude, where temperature and pressure create conditions that allow aluminum oxide to condense from vapor into solid crystal, a boundary layer in the atmosphere where the transition happens continuously. Above this layer, the atmosphere becomes too hot and aluminum oxide remains entirely gaseous, individual atoms of aluminum and oxygen floating separately in the superheated air. Below this layer, the temperature rises again due to increasing pressure and proximity to the planet's heat source, causing any crystals that fall to evaporate back into gas before they can descend much farther. The cloud layer represents a sweet spot, a zone where conditions permit the temporary existence of solid corundum suspended in the thick atmosphere of this alien world. The formation process begins with aluminum and oxygen atoms combining in the cooling upper atmosphere, the chemical bonds forming as thermal energy decreases enough to permit molecular stability. The first molecules cluster together, creating tiny seed crystals, perhaps only nanometers across. far too small to see individually, but present in vast numbers throughout the cloud layer. These seed crystals attract additional aluminum oxide molecules from the surrounding vapor, growing slowly as material accumulates on their surfaces, building up layer by atomic layer. The growth continues as long as conditions remain favorable, temperature and pressure maintaining the right balance to permit solid crystal formation. The crystals take on the characteristic structure of corundum, the hexagonal crystal system that creates the hardness and optical properties sapphires and rubies display on Earth. The atomic arrangement follows precise geometric rules, aluminum and oxygen atoms locking into position in patterns that repeat throughout the crystal lattice, creating structures that would appear perfectly ordered if we could observe them at atomic scale. The crystal faces develop as growth proceeds, flat surfaces forming along specific crystallographic planes, creating the faceted appearance that gives gemstones their distinctive look. These microscopic crystals, though far smaller than any gemstone a jeweler would recognize, possess the same fundamental structure and composition as the sapphires mined from Earth's crust. The size of the crystals varies throughout the cloud layer, with the smallest remaining suspended almost indefinitely, while larger crystals begin to experience enough gravitational pull to overcome the atmospheric turbulence, keeping them aloft. A typical crystal might measure only a few micrometers across, about the width of a bacterial cell, though some regions might produce larger crystals reaching tens or even hundreds of micrometers. The size distribution follows patterns determined by how long crystals have had to grow and how conditions vary within different parts of the cloud deck. Regions where vapor concentration runs higher and temperature sits right at the condensation point produce the largest and most numerous crystals, creating zones of particularly dense gemstone haze. The light interacting with these countless tiny crystals creates optical effects that transform the appearance of the cloud layer into something unlike any terrestrial sky. Each crystal acts as a tiny prism and mirror, refracting starlight that passes through it and reflecting light from its faceted surfaces, scattering illumination in multiple directions. The combined effect of billions of crystals creates a shimmering iridescence, the clouds appearing to glow with an internal light that shifts and changes as the crystals rotate and tumble in the atmospheric currents. The blue color deepens or lightens depending on crystal size and concentration, with dense regions appearing almost sapphire solid, while thinner areas show paler, more translucent hues. The metallic quality of the shimmer comes from the high refractive index of corundum, the way aluminum oxide bends light, creating particularly bright reflections compared to water ice or other common cloud materials. The crystals catch starlight from the nearby sun and transform it, splitting white light into component colors and redirecting it at angles that create rainbow effects and bright spots throughout the cloud deck. Some crystals align with their longest axis vertical due to aerodynamic forces as they fall, creating preferential scattering directions that produce halos and light pillars similar to those ice crystals create in Earth's atmosphere, but rendered in sapphire blue instead of white. The clouds drift horizontally as well as evolving vertically, carried by winds that flow at speeds far exceeding anything Earth's atmosphere produces. The motion creates streaming patterns, long trails of gemstone vapor and crystal, extending across hundreds or thousands of kilometers, marking the paths of jet streams and atmospheric circulation cells. The crystals move with the wind, their small size meaning they respond quickly to air currents, following the flow without significant lag. The wind patterns visible in the cloud structure reveal the complex atmospheric dynamics operating on this world. The motion, driven by temperature differences between the day side and night side of this tidally locked planet. The density of the atmosphere at this altitude, far greater than Earth's air at any height, provides enough buoyancy to suspend crystals much larger than would be possible in our thinner atmosphere. The thick gas, composed primarily of hydrogen and helium, but containing significant fractions of heavier elements, creates viscous resistance to falling particles, slowing their descent and allowing them to remain airborne longer. A crystal that would fall rapidly through Earth's air drifts slowly here. Its descent measured in meters per hour rather than meters per second. The journey from cloud formation altitude to deeper atmospheric layers, taking hours or even days, depending on crystal size and atmospheric conditions. Temperature at the cloud deck hovers around 2,500 degrees Celsius, hot enough to glow dull red if we could see thermal radiation directly, though our viewpoint filters out the infrared and shows only the visible starlight scattered by the crystals. This temperature, impossibly hot by Earth standards, represents a relatively cool layer in this planet's atmosphere, a region where heat has radiated away enough to permit even this limited condensation. Higher up, temperatures climb higher still, approaching 3,000 degrees, where stellar radiation bathes the uppermost atmosphere. Lower down, compression, heating, and proximity to the planet's interior drive temperatures back upward, creating the thermal structure that permits this narrow cloud zone to exist. The crystals forming around us represent a transition state, solid matter existing temporarily in an environment dominated by gas. A brief interlude in the cycle that continuously transforms aluminum oxide between its vapor and solid forms. The formation we observe now will not persist indefinitely, as changes in temperature or pressure or atmospheric circulation will eventually evaporate these crystals back into gas or carry them to regions where they cannot remain solid. The cloud deck exists in dynamic equilibrium, crystals forming at the rate they evaporate elsewhere, the total amount of solid corundum remaining roughly constant even as individual crystals come and go. The scale of this cloud system dwarfs anything Earth produces, with the gemstone haze extending across the entire day side and wrapping partially around to the night side of the planet. The total mass of aluminum oxide crystals suspended in the atmosphere at any given moment likely exceeds millions of tons, though this represents only a tiny fraction of the planet's total atmospheric mass. The clouds form preferentially in certain regions where temperature and circulation patterns create optimal conditions, producing variations in density and coverage that create weather patterns visible from space. An observer watching from a distance would see bright and dark regions shifting across the planet's face, the changing cloud cover reflecting different amounts of starlight. The experience of floating here among these metallic blue clouds creates a sense of profound alienness, the realization settling in that we have entered an environment where the familiar materials of Earth exist in unfamiliar forms and states. The gemstones that we value as rare and precious on our world form here spontaneously and continuously, condensing from atmospheric vapor as naturally as water droplets form in Earth's clouds. The scale transforms scarcity into abundance, turning what represents wealth and rarity at home into mere atmospheric chemistry here. Billions of tiny sapphires and rubies existing as weather rather than treasure. The beauty remains, perhaps intensified by the sheer quantity and the alien context, the shimmer and color-creating vistas that no Earth sky can match. And now, suspended in this impossible atmosphere among clouds of vaporized gemstone, we watch as the process continues, as crystals grow and begin their descent, starting the journey that will carry them deeper into the planet's atmosphere, toward a fate we will follow shortly. The rain begins with individual crystals, achieving enough size to overcome atmospheric turbulence, starting their slow fall through the thick air, their faceted surfaces catching light as they tumble and spin in their descent. The fall represents only the first stage of a longer cycle, a journey through changing conditions that will transform these solid crystals back into the vapor from which they formed, completing the loop that defines weather on this distant world. The journey of a single corundum crystal from the moment of formation to its eventual return to vapor state tells the story of how weather works on HAT-P-7b, revealing the cycles that move material through the atmosphere and the extreme conditions that permit gemstones to exist as precipitation. We follow one crystal now, a microscopic sapphire perhaps 5 micrometers across, its hexagonal structure perfect at the atomic level. Its blue color derived from iron atoms substituting for aluminum in a few scattered positions throughout the lattice. This crystal formed minutes ago in a region where temperature dropped just low enough to permit condensation, and it has grown by accumulating additional aluminum oxide from the surrounding vapor until reaching a size where gravity begins to win against the atmospheric turbulence, keeping smaller crystals aloft. The initial descent proceeds slowly, the crystal falling at perhaps a few centimeters per second through the thick atmosphere, its small size and relatively low density compared to the surrounding gas, creating substantial drag resistance. The air, though far thinner than liquid, flows around the crystal like a viscous fluid due to the density and pressure at this altitude. The hydrogen and helium molecules bumping against the crystal's faceted surfaces thousands of times per second. Each collision transfers tiny amounts of momentum, creating resistance that opposes the gravitational pull, drawing the crystal downward. The net effect keeps the fall rate much slower than it would be in a vacuum or even in Earth's atmosphere, giving the crystal time to interact with changing conditions as it descends. The temperature gradient in this region of the atmosphere runs counter to what Earth's troposphere demonstrates, with temperature actually increasing with depth rather than decreasing. The compression of gas under its own weight, creating heating that overwhelms the cooling effect of distance from the internal heat source. Our falling crystal descends into warmer air, the temperature rising from the 2,500 degrees where it formed toward higher temperatures deeper in the atmosphere. This increasing temperature creates a problem for the crystal's continued existence. As aluminum oxide solid form becomes unstable above certain temperatures, the thermal energy becoming sufficient to break the bonds holding atoms in the crystal lattice and returning them to vapor state. The crystal survives the first 100 meters of descent without significant change, the temperature increase remaining small enough that the crystal maintains its structure intact. The faceted surfaces show no signs of melting or sublimation, the atomic lattice holding firm against the thermal bombardment from surrounding gas molecules. The blue color remains constant, the iron impurities staying locked in their substitutional positions within the aluminum oxide structure. The crystal tumbles slowly as it falls, its asymmetric shape creating uneven aerodynamic forces that cause rotation, the facets catching and releasing light in rhythmic flashes as the crystal spins through the thick air. But as the descent continues and depth increases, the temperature begins to approach the threshold where solid corundum cannot persist in equilibrium with the surrounding vapor pressure. At around 2,600 degrees Celsius, the crystal's surface begins to sublime. Aluminum oxide molecules breaking free from the lattice and entering the gas phase directly without passing through a liquid state. The sublimation starts at crystal defects and edges where atoms are less tightly bound, creating slight irregularities in the previously smooth faceted surfaces. The rate of mass loss remains small initially, only a few molecular layers per minute evaporating away, but the process accelerates as temperature continues to rise with increasing depth. The crystal shrinks as it falls, losing mass from its surface while gravity continues pulling the remaining solid material downward. The shrinkage does not proceed uniformly across all surfaces, as different crystal faces have different atomic arrangements, and therefore different sublimation rates, causing the crystal shape to evolve as it descends. Corners and edges vanish first, the high-energy positions where atoms are least stable evaporating preferentially, rounding the formerly sharp geometric form. The blue color may intensify if iron-containing regions sublime more slowly than pure aluminum oxide regions, or it may fade if the impurities evaporate preferentially, the changing composition altering the optical properties. Within another 100 meters of descent, the temperature rises above 2,700 degrees, and the sublimation rate increases dramatically, the crystal now losing mass faster than it falls, shrinking visibly if we could observe at this scale. The organized atomic lattice that characterized the corundum crystal breaks down progressively from the outside inward, each surface layer evaporating and adding aluminum and oxygen atoms back into the surrounding atmosphere. The geometric form that took minutes to build through accretion dissolves in seconds of exposure to this higher temperature environment, the careful atomic arrangement giving way to random thermal motion. And then, within a few hundred meters total descent from the cloud layer, the crystal ceases to exist as a distinct solid object, the last few molecules evaporating and leaving only gas where a sapphire once tumbled through the atmosphere. The aluminum and oxygen atoms that briefly combined to form a crystal now float separately again, indistinguishable from all the other aluminum and oxygen in this region of the atmosphere, the temporary organization into solid form erased by heat. The crystal's brief existence, from condensation to evaporation, spanned perhaps 20 or 30 minutes, a short-lived precipitation event that never reached more than a few hundred meters from its formation altitude before returning to vapor. This cycle represents the typical fate of corundum crystals forming in the cloud deck, a continuous precipitation process that sees crystals rain downward only to evaporate before descending very far, creating a steady flux of material from vapor to solid and back to vapor within a relatively narrow atmospheric layer. The evaporated material does not disappear from the system, but remains in the atmosphere, available to condense again if it reaches regions where temperature permits. The atmospheric circulation carries the vapor horizontally and vertically, mixing it through different temperature zones and creating opportunities for repeated cycles of condensation and evaporation as the same aluminum and oxygen atoms participate in crystal formation multiple times. In some regions of the atmosphere, the temperature gradient or wind patterns create conditions where crystals can fall farther before evaporating, descending hundreds or even thousands of meters through layers where sublimation rates remain low enough to permit survival. These longer-lived crystals grow larger during their extended lifetimes, accumulating more material as they fall through vapor-rich regions, reaching sizes that would make them visible to the naked eye if we could observe them directly. A crystal that survives to 10 or 20 micrometers diameter becomes a substantial sapphire by atmospheric standards. A grain large enough to scatter light efficiently and contribute significantly to the cloud's optical properties. The largest crystals, those rare individuals that form under particularly favorable conditions and follow descent paths through cooler than average air, might survive long enough to reach deeper atmospheric layers, where the temperature curve reverses and begins to decrease again with depth due to changing atmospheric composition and radiative effects. These crystals enter a region where they stop shrinking and begin growing again, accumulating material as they encounter vapor-rich air at temperatures low enough to permit condensation. The crystals might bounce through several cycles of growth and sublimation as they encounter varying conditions, their size fluctuating as environmental factors shift during their prolonged atmospheric journey. But eventually, all crystals face the same fate of evaporation, as the lower atmosphere where they might fall eventually becomes hot enough that no crystal can survive regardless of size or trajectory. The base of the atmosphere, hundreds or thousands of kilometers below the cloud deck, maintains temperatures of 3,000 degrees or higher, conditions that vaporize not just aluminum oxide, but most other compounds that might condense at higher altitudes. No rain reaches this region, no precipitation survives the heat, and the distinction between atmosphere and planetary interior becomes blurred as gas transitions gradually to supercritical fluid and then to liquid under extreme pressure. The cycle operates in reverse as well, with vapor rising from deeper atmospheric layers, carried upward by convection and circulation patterns, the ascending air cooling as it rises and pressure decreases. The cooling allows condensation when temperature drops below the threshold for solid corundum stability, creating new crystals at high altitude that will then begin their own descent and evaporation cycle. The upward flow of vapor and downward rain of crystals creates a circulation cell in the vertical dimension, material cycling through the cloud layer repeatedly over timescales of hours to days, depending on wind speeds and atmospheric dynamics. The horizontal motion adds another dimension to the crystal journey, as powerful winds carry both vapor and crystals sideways faster than they move vertically, creating trajectories that spiral or curve rather than dropping straight down. A crystal might form on the night side of the planet, where cooler temperatures permit condensation at lower altitudes than on the day side, then be carried toward the day side by circulation patterns, encountering warmer air as it approaches the intensely heated sunlit hemisphere. The increasing temperature as the crystal moves horizontally causes evaporation even if the crystal maintains constant altitude, the changing conditions along its wind-driven path ultimately determining its fate. The effect creates patterns in the cloud distribution, with thicker cloud decks on the night side, where cooler temperatures permit more crystal formation and longer crystal lifetimes, while the day side shows thinner or more broken clouds, where heat limits crystal survival. The transition zone between night and day displays complex structure as crystals carried from cool regions encounter warm air and begin to evaporate, creating a boundary layer where precipitation rates peak as crystals that survived formation on the night side finally succumb to heat as they approach the day side. The visual effect from a distance shows asymmetric cloud cover, more reflective night-side regions contrasting with darker day-side areas where fewer crystals exist to scatter starlight. Some regions of the atmosphere show conditions that permit suspended crystal layers rather than falling precipitation, zones where upward air motion exactly balances crystal fall velocity, keeping particles hovering at constant altitude for extended periods. These suspension layers create particularly bright cloud features as crystals accumulate in the region where forces balance, creating high concentrations of reflective particles that scatter light efficiently. The layers shift and move with changing wind patterns, but maintain their existence as long as the vertical air motion persists, creating semi-permanent cloud structures that become long-lived features in the planet's atmosphere. The total mass of aluminum oxide cycling through this precipitation process represents only a tiny fraction of the element's abundance in the planet's atmosphere, as most aluminum exists in vapor form at all altitudes, rather than condensing into crystals. The ratio of solid to vapor varies with temperature and pressure, with perhaps 1 part in a million of the atmospheric aluminum existing as solid at any moment in the cloud layer, while the vast majority remains gaseous. This small fraction, nonetheless, creates visible clouds because even trace amounts of reflective crystals scatter light efficiently. And the sheer scale of the atmosphere means that 1 in a million fraction still represents billions of tons of crystalline material suspended or falling at any given time. The energy driving this cycle comes ultimately from the star HAT-P-7, whose radiation heats the day side of the tidally locked planet, creating temperature differences that drive atmospheric circulation and vertical motion that carries material through different temperature zones. The cycle cannot operate without this energy input, as the convection and wind patterns required to move material between regions of different temperature depend on continued heating to maintain the temperature gradients. The precipitation represents a way for the atmosphere to transport heat, as the phase changes between vapor and solid absorb and release energy, moving heat content along with material as crystals form in cool regions and evaporate in warm regions. And so the gemstone rain continues, crystals forming and falling and evaporating in endless repetition, the cycle proceeding without interruption day and night, though the rates and locations vary with local conditions and atmospheric dynamics. The sapphires and rubies that form here exist only briefly, their solid state representing a temporary organization of atoms that will inevitably return to chaos as heat reclaims the energy temporarily stored in crystalline bonds. The beauty of their existence comes partly from this impermanence, the knowledge that each crystal's faceted perfection lasts only minutes before dissolving, making the rain a constant renewal, a continuous creation and destruction of tiny gemstones in the alien sky. The heat that vaporizes corundum crystals and maintains the extreme conditions throughout HAT-P-7b's atmosphere comes from proximity to one of the galaxy's many stars, but the specific temperature achieved on this planet exceeds what distance alone would predict, reaching levels that transform solid rock into atmospheric vapor and push the planet into a regime of chemistry and physics that Earth never approaches. The dayside temperature, the scorching heat that dominates the hemisphere permanently facing the star, reaches approximately 2,800 degrees Celsius, a figure that translates to about 5,000 degrees Fahrenheit, placing this world among the hottest planets ever discovered. Numbers alone fail to capture what such heat means, but examining its effects on matter and comparing it to familiar reference points begins to make the extremity tangible. At 2,800 degrees, iron melts and begins to boil, transitioning from solid metal to liquid and then to vapor as thermal energy overcomes the metallic bonds holding atoms together. The melting point of iron sits at 1,538 degrees Celsius, well below HAT-P-7b's dayside temperature, meaning that metallic iron cannot exist in solid form anywhere in the upper atmosphere of this planet. Steel, bronze, copper, aluminum, and most other familiar metals also exist only as vapor, or perhaps as liquid droplets in slightly cooler regions. The atomic arrangements that give metals their strength and conductivity, unable to persist when every atom vibrates with enough energy to break free from its neighbors. Rock materials fare no better under these conditions, as silicate minerals that compose most rocky planets begin to melt at temperatures between 1,000 and 2,000 degrees, depending on composition, transforming into lava at pressures and temperatures far below what HAT-P-7b experiences. The basalts that form Earth's oceanic crust and volcanic islands, solid and strong under terrestrial conditions, would flow as glowing liquid on HAT-P-7b's dayside, unable to cool enough to solidify. Even granite, which melts at slightly higher temperatures than basalt, cannot maintain solid form in this environment, reducing to a silicate vapor or droplet suspended in the atmosphere. The planet likely possesses no solid surface at all in the conventional sense, no crust of rock to walk upon, only gas transitioning gradually to liquid under increasing pressure deeper in the atmosphere. The heat creates a thermal radiation spectrum that includes visible light, meaning the planet glows dimly red from its own temperature, adding its own emission to the reflected starlight that dominates its appearance. Objects at 2,800 degrees emit primarily in the infrared portion of the spectrum, the peak wavelength sitting around 1,000 nanometers, but the emission spectrum extends into the red visible range, starting around 700 nanometers, creating a faint, ruddy glow. An observer viewing HAT-P-7b from space would see it as a dim red object, even without starlight, the thermal emission providing enough visible light to make the planet perceptible against the darkness, though far dimmer than the star it orbits. The night side, cooler but still around 1,500 degrees, glows even more faintly, a deep red barely distinguishable from black, without sensitive instruments. This temperature, results from HAT-P-7b's orbital characteristics, specifically the planet's extreme proximity to its star HAT-P-7, with the orbital distance measuring only 0.0379 astronomical units, or about 3.5 million miles. For comparison, Mercury orbits the Sun at 0.39 astronomical units, more than 10 times farther than HAT-P-7b orbits its star, making this planet's orbit tighter than any in our solar system. The inverse square law governing radiation intensity means that HAT-P-7b receives more than 100 times the energy per unit area that Mercury receives. The closeness to the star creating an intensity of illumination and heating that has no solar system analogue. The star HAT-P-7 itself contributes to the extreme heating by being brighter and hotter than our Sun. Classified as an F-type main sequence star with a surface temperature around 6,350 degrees Kelvin compared to the Sun's 5,778 degrees. The higher temperature means HAT-P-7 emits more energy per unit surface area and also shifts its peak emission towards shorter wavelengths in the blue-white portion of the spectrum, rather than the yellow wavelengths where the Sun peaks. The total luminosity of HAT-P-7 exceeds the Sun's by a factor of about 4, meaning it puts out 4 times as much total energy, despite being only moderately larger in physical size, around 1.5 times the Sun's radius. The combination of close orbit and bright star creates the furnace conditions that characterize HAT-P-7b's environment. The stellar radiation arriving with enough intensity to heat the dayside atmosphere to temperatures where molecular bonds break, and most materials exist only as individual atoms or simple molecules. The heating penetrates deep into the atmosphere because the intense, short-wavelength radiation from the F-type star includes significant ultraviolet light that molecules absorb efficiently, depositing energy throughout the atmospheric column rather than just heating the surface. The result creates a temperature structure different from planets farther from their stars, with the upper atmosphere heated directly by stellar radiation to extremely high temperatures, while deeper layers heat through compression and downward energy transport. The tidal locking that keeps one hemisphere permanently facing the star results from the same proximity that creates the extreme heating. As the star's gravity raises enormous tides in the planet's atmosphere and potentially in its interior, creating friction that gradually slowed the planet's rotation over millions of years until the rotation period matched the orbital period. Once locked, the planet maintains this orientation indefinitely, barring some catastrophic disturbance, creating permanent day and night hemispheres with vastly different temperatures. The dayside receives continuous stellar radiation year-round, the star never setting, never allowing the surface to cool through nighttime radiative loss. The night side receives no direct starlight, radiating its heat into space without replacement, except through atmospheric transport from the dayside. The temperature difference between day and night, roughly 1,300 degrees, represents the driving force for the powerful winds that circulate around the planet, carrying heat from the sunlit hemisphere to the dark hemisphere, and creating the dynamic atmosphere that moves gemstone vapor through condensation and evaporation cycles. The temperature gradient creates pressure gradients that accelerate atmospheric gas from high pressure on the hot day side to lower pressure on the cooler night side, the flow achieving supersonic velocities as gas rushes to equalize the imbalance. The circulation never achieves equilibrium because the stellar heating continually maintains the temperature difference, ensuring that winds persist indefinitely as long as the star shines. Despite the night side receiving no direct starlight, its temperature remains far above what radiative cooling alone would produce, staying at 1,500 degrees rather than dropping to the near absolute zero temperatures that would characterize an unheated surface in deep space. The atmospheric circulation carries enough heat from day side to night side to maintain these elevated night side temperatures. The winds, acting as a heat transport mechanism that distributes stellar energy around the entire planet. The efficiency of this heat transport determines the actual night side temperature, with faster winds and more vigorous circulation creating more uniform temperatures between hemispheres, while weaker circulation would allow larger day-night temperature differences. The heat also affects the planet's structure at deeper levels, as the extreme temperatures at the top of the atmosphere imply even higher temperatures deeper down, where pressure compresses gas and generates additional heat through compression. The atmospheric temperature likely increases with depth initially, rising from the 2,800 degrees at the top to perhaps 3,000 degrees or more, hundreds of kilometers down, before eventually peaking and beginning to decrease if a transition to liquid or supercritical fluid phase occurs. The exact temperature profile depends on atmospheric composition, greenhouse effects from various molecules absorbing infrared radiation, and the planet's internal heat content left over from formation and generated by ongoing tidal heating from the star's gravity. The greenhouse effect operates powerfully on HAT-P-7b, despite the extreme temperatures, as molecules in the atmosphere absorb the planet's thermal infrared emission and re-radiate it in all directions, including back downward, trapping heat and elevating temperatures above what pure radiative balance would produce. Water vapor, carbon dioxide, and methane that create greenhouse warming on Earth likely do not survive in molecular form at HAT-P-7b's temperatures. But other molecules, including titanium oxide, vanadium oxide, and various metal hydrides, absorb infrared radiation efficiently and create greenhouse heating at high temperature. The cumulative effect of these high-temperature greenhouse gases probably elevates the dayside temperature by hundreds of degrees above what it would be without atmospheric absorption. The heat creates an environment completely incompatible with any form of life as we understand it, as the temperatures denature proteins instantly, vaporize water, and break apart the complex organic molecules that biological chemistry requires. No liquid water can exist on HAT-P-7b, as water at these temperatures exists only as superheated steam, dissociated into hydrogen and oxygen atoms, or possibly as trace constituents of solid materials in the deepest atmospheric layers, where pressure might permit exotic chemistry. The concept of a habitable zone, the orbital distance where liquid water could exist on a planet's surface, sits far from HAT-P-7b's actual orbit, likely around 0.5 to 1.0 astronomical units from HAT-P-7, more than 10 times farther from the star than this scorched world circles. The study of such extreme temperatures expands our understanding of planetary atmospheres and thermal processes, revealing how matter behaves under conditions impossible to replicate in terrestrial laboratories, except in the most sophisticated, high-energy physics facilities. The temperatures on HAT-P-7b exceed those in blast furnaces, arc welders, and most industrial processes, approaching the conditions inside stars, though still far below the millions of degrees required for nuclear fusion. Observing how real planets respond to such extreme heating, what molecules survive, how atmospheres circulate, and what chemistry occurs provides data that tests our theoretical models and extends our knowledge beyond the relatively mild conditions that characterize Earth and most solar system planets. And these temperatures, fierce enough to vaporize rock and boil iron, create the conditions necessary for the exotic weather we observe. The gemstone clouds and corundum rain that exist because aluminum oxide can briefly condense in slightly cooler regions before evaporating again in the relentless heat. The temperature becomes not just a hostile condition, but the fundamental parameter that defines this world's nature, determining what materials can exist in what forms, and creating the extreme environment that makes HAT-P-7b simultaneously hostile and remarkable. A place where heat transforms everything it touches, and yet permits beauty in the form of floating sapphire crystals that shimmer in the star's harsh light before vanishing back into vapor. The heat differences between HAT-P-7b's dayside and nightside, the 1300-degree temperature gap between the star-facing hemisphere and the perpetually dark hemisphere, create atmospheric motions so powerful that they rank among the most extreme winds observed on any planet in the galaxy. The atmosphere, unable to remain still under such dramatic temperature and pressure gradients, accelerates to hypersonic speeds as gas flows from the scorching dayside toward the cooler nightside, creating wind patterns that dwarf even the fiercest hurricanes and tornadoes Earth produces. The fastest winds reach approximately 5,000 miles per hour, a velocity that translates to about 8,000 kilometers per hour, or more than 6 times the speed of sound in Earth's atmosphere at sea level. To understand what 5,000 mile per hour winds mean requires comparison to familiar velocities and exploring what such motion would do to any object in its path. Earth's fastest sustained winds occur in tornado cores and the eye walls of the most intense hurricanes, reaching maximum speeds around 300 miles per hour before the storm's structure becomes unsustainable. A tornado with 200 mile per hour winds destroys well-built homes, strips pavement from roads, and carries automobiles through the air like leaves. The kinetic energy in the wind sufficient to overcome the structural integrity of nearly anything humans construct. HAT-P-7b's winds blow 16 times faster than these most extreme terrestrial winds, carrying correspondingly more kinetic energy and demonstrating forces that would obliterate any material object instantly. The wind speed also exceeds the speed of sound by a large margin, creating supersonic flow throughout much of the atmosphere, a condition that generates shock waves and fundamentally changes how the atmosphere behaves. When gas flows faster than the speed at which pressure disturbances propagate through it, compression waves cannot move upstream to warn the oncoming gas about obstacles or pressure changes ahead, causing the flow to pile up abruptly in shock fronts where pressure, temperature, and density change discontinuously over distances of only a few molecular mean-free paths. These shock waves crisscross HAT-P-7b's atmosphere wherever flow conditions change. creating regions of sudden compression, heating that add to the already extreme temperatures and generate acoustic energy that would create deafening noise if sound could propagate to a listener. The atmospheric circulation pattern that produces these winds follows a relatively simple structure driven by the temperature difference between hemispheres, though complications arise from the planet's rotation, atmospheric composition variations, and turbulent mixing. The basic pattern resembles a giant convection cell wrapping around the planet, with hot gas rising on the day side, where stellar heating creates thermal buoyancy, flowing horizontally toward the night side at high altitude, descending on the night side where cooling increases gas density, and returning at lower altitude toward the day side to complete the loop. This meridional circulation, flowing from equator to poles and back in latitude bands, in addition to the day-night flow, creates a complex three-dimensional wind pattern that varies with altitude and latitude. The strongest winds occur in narrow jet streams, bands of particularly fast-flowing air, similar to Earth's jet streams, but operating at far higher velocities and driven by much larger temperature differences. These jets circle the planet roughly along the equator, and at mid-latitudes, forming zones where wind speed peaks and creating boundaries between air masses moving at different velocities. The equatorial jet receives particular attention from astronomers because it creates observable effects on the planet's brightness, as seen from Earth. The fast-moving air carrying hot regions and cloud patterns past the terminator between day and night, creating variations in how much starlight the planet reflects that observers can detect from across interstellar distances. The rotation of HAT-P-7b, though tidally locked to its star, and thus rotating far more slowly than Earth, still affects the wind patterns through the Coriolis effect, the apparent deflection that occurs when air moves across a rotating reference frame. The planet completes one rotation every 2.2 days, the same period as its orbit around the star, maintaining the tidal lock that keeps one face toward the star. This relatively slow rotation compared to Earth's 24-hour day means the Coriolis effect operates more weakly than on Earth. But the immense wind speeds and large planetary size mean the deflection still influences flow patterns significantly. Air moving from dayside to nightside curves westward in the planet's northern hemisphere and eastward in the southern hemisphere, creating spiral patterns in the atmospheric flow, similar to the cyclonic spirals that characterize Earth's weather systems, but operating at vastly different scales. The wind shear, the change in wind velocity with altitude and latitude, creates turbulence throughout the atmosphere as adjacent air masses, moving at different speeds, mix across their boundaries. Turbulent eddies ranging from centimeters to thousands of kilometers in size form and dissipate continuously, transferring momentum and energy between different atmospheric layers and creating the chaotic, small-scale flow that coexists with the organized, large-scale circulation. The turbulence affects cloud formation and distribution by mixing air masses with different temperatures and compositions, creating regions where conditions favor gemstone crystal nucleation and growth, and other regions where crystals cannot form or survive. The energy contained in these winds represents a significant fraction of the total energy the planet receives from its star, with perhaps 10 to 20% of the incoming stellar radiation converted into kinetic energy of atmospheric motion rather than simply heating the gas. This conversion efficiency, far higher than Earth's atmosphere achieves, results from the extreme temperature gradient and the minimal friction that slows winds in HAT-P-7b's thick but smooth atmosphere, where no surface features or ground friction exists to dissipate kinetic energy. The winds, once accelerated, maintain their velocity until the energy dissipates through turbulent cascade to smaller scales, or through molecular viscosity, converting kinetic energy to heat at the smallest scales of motion. The supersonic velocities mean that the atmosphere behaves differently from subsonic flows in several important ways, beyond just shockwave formation. The relationship between pressure and velocity changes, with supersonic gas experiencing pressure increases when forced to slow down rather than pressure decreases, the opposite of what happens in subsonic flow. This counterintuitive behavior affects how gas flows around obstacles and through varying cross-sections, creating expansion fans where subsonic flow would compress, and creating compression where subsonic flow would expand. The result complicates atmospheric modeling and creates flow structures that don't exist in Earth's subsonic wind patterns. The gemstone clouds discussed earlier move with these powerful winds, carried along at speeds matching the atmospheric velocity at the altitude where they form. The small crystals responding almost immediately to air motion due to their minimal mass and large surface area relative to their weight. A crystal forming on the night side travels toward the day side at thousands of miles per hour, crossing the terminator and entering progressively warmer air, where it begins to evaporate. Its lifespan determined partly by how quickly the wind carries it into regions where temperature exceeds the stability threshold for solid corundum. The wind patterns create streaking features in cloud distribution, long trails of crystals extending downstream from formation regions, marking the high-velocity flow, like contrails mark aircraft paths in Earth's sky. The vertical component of wind velocity, the speed at which air moves upward or downward, reaches hundreds of miles per hour in regions of strong convection, creating powerful updrafts that lift material from deep atmospheric layers to high altitudes and downdrafts that pull material downward. These vertical winds affect crystal fall velocities significantly. As a crystal experiencing 100 miles per hour, updraft effectively falls more slowly or even moves upward relative to the ground, while crystals in downdrafts accelerate downward faster than gravity alone would pull them. The interplay between vertical winds and crystal settling creates complex spatial patterns in where rain reaches deep atmospheric layers versus where it remains suspended or rises despite its weight. The sound of these winds, if sound could propagate to a listener capable of surviving in this environment, would likely be a continuous, deafening roar from the turbulence and shock waves. The acoustic energy creating pressure oscillations far exceeding the threshold of pain for human hearing. The sound intensity would reach levels typically associated with rocket launches or nearby lightning strikes, but sustained continuously rather than appearing in brief pulses, creating a sonic environment as hostile as the heat and pressure. The frequency spectrum would cover a broad range from deep infrasonic rumbles at frequencies below human hearing to high-pitched screams at ultrasonic frequencies above human perception. The full spectrum of atmospheric turbulence manifesting as acoustic energy propagating through the dense gas. The persistence of these wind patterns over years and decades demonstrates the stability of HAT-P-7b's atmospheric circulation, despite the extreme velocities and turbulent character. Observations spanning multiple years show that while small-scale details change constantly, the large-scale pattern of day-to-night flow and equatorial jets remains consistent, the temperature gradient continuing to drive the same basic circulation structure year after year. This stability suggests that despite the violence of the individual gusts and turbulent eddies, the overall system operates in a quasi-steady state. Energy input from stellar heating, balancing energy dissipation through friction and turbulent mixing, maintaining a rough equilibrium in the atmospheric dynamics. The study of these extreme winds expands our understanding of atmospheric dynamics and tests our computational models of fluid flow under conditions far more extreme than Earth demonstrates. The equations governing atmospheric motion apply regardless of wind speed or temperature. The laws of physics operating identically on HAT-P-7b as on Earth. But the solutions to those equations under extreme conditions reveal behaviors and structures that mild Earth-like conditions never produce. The supersonic flows, the powerful jets, the hypersonic velocities all follow from the same fundamental principles that govern gentle breezes and afternoon thunderstorms, demonstrating how the same physical laws produce radically different outcomes depending on the boundary conditions and forcing mechanisms. And these winds, fierce enough to tear apart any material, powerful enough to circulate the planet's entire atmosphere multiple times per week, fast enough to outrace the speed at which sound travels, represent the third character in the story of HAT-P-7b's weather, alongside the gemstone clouds and the relentless heat, the three elements combining to create an environment utterly unlike anywhere else we know, a place where beauty and violence coexist in the endless cycling of aluminum oxide between vapor and crystal forms, carried by winds that would sound like endless thunder if anyone could hear them, driven by heat that would vaporize the listener long before the sound arrived. The atmosphere of HAT-P-7b, extending from the thin outer envelope where stellar radiation directly strikes, to the deep compressional layers where conditions transition toward the planetary interior, possesses a vertical structure as complex as its horizontal wind patterns, with distinct layers characterized by different temperatures, pressures, chemical compositions, and physical processes. Understanding this vertical architecture requires building a mental model of the atmosphere from the top down, exploring each layer in sequence and examining how they connect to create the complete atmospheric column that defines this world's outer envelope. The topmost layer, barely qualifying as atmosphere at all, consists of extremely thin gas extending thousands of kilometers above where appreciable density ends, a region where individual atoms and molecules rarely collide with each other, and where the concept of temperature becomes ambiguous. This outermost region, called the exosphere in atmospheric science terminology, represents the transition between atmosphere and interplanetary space, a boundary zone where escaping particles leave the planet's gravitational influence permanently, and where incoming stellar radiation and charged particles first interact with planetary matter. The gas density here measures only thousands of atoms per cubic centimeter, compared to the 10 billion atoms per cubic centimeter that compose Earth's sea level air, making this region effectively vacuum by terrestrial standards, though still containing enough matter to absorb ultraviolet radiation and glow faintly when ionized. The temperature in this region can reach thousands or even tens of thousands of degrees, as energetic photons from the star heat the sparse gas, though the low density means the total heat content remains negligible despite the high temperature. Below the exosphere, at altitudes around 1,000 kilometers above where the cloud deck forms, the atmosphere thickens enough to begin behaving as a continuous fluid rather than as individual particles on ballistic trajectories, marking the beginning of what atmospheric scientists call the thermosphere. This region shows rapidly increasing density with decreasing altitude, following an exponential relationship where each 10 or 20 kilometers of descent roughly doubles the gas concentration, creating a gradual transition from near vacuum to appreciable atmosphere. The temperature remains very high throughout the thermosphere, sustained by the absorption of stellar ultraviolet and X-ray radiation by atmospheric atoms and molecules, keeping the gas energized despite the increasing density that would normally lead to cooling through expansion. The chemical composition in these upper layers differs significantly from the deeper atmosphere because lighter elements and molecules dominate where gas is thin enough that gravity has partially separated different species by mass, a process called gravitational settling. Hydrogen, being the lightest element and the most abundant in HAT-P-7b's composition, concentrates in the upper atmosphere preferentially, while heavier molecules like titanium oxide and aluminum oxide remain at lower altitudes where their greater mass causes them to settle. The separation is not perfect, as turbulent mixing from winds and convection continuously stirs the atmosphere and prevents complete stratification. But enough separation occurs that the chemical makeup shifts measurably with altitude through the thermosphere and exosphere, descending through several hundred kilometers of steadily thickening atmosphere. We approach the altitude where temperature begins to decrease with decreasing height, marking the transition from thermosphere to mesosphere. Though these traditional atmospheric layer names apply imperfectly to an atmosphere so different from Earth's. This transition occurs where radiative cooling begins to overcome the heating from stellar radiation absorption, creating a temperature maximum around 500 to 1,000 kilometers altitude, depending on stellar activity and atmospheric conditions. Below this altitude, temperature drops as the atmosphere becomes thick enough that gas cannot efficiently radiate away the heat it receives, creating a region where convection begins to operate and vertical mixing starts to dominate over radiative processes. The mesosphere on HAT-P-7b extends from this upper boundary down to perhaps 50 to 100 kilometers above the cloud deck, a thick layer where temperature decreases steadily with decreasing altitude and where the atmosphere begins to show the chemical complexity that characterizes the lower regions. Metal oxides, including titanium oxide, vanadium oxide, and aluminum oxide, begin to appear in appreciable concentrations in the lower mesosphere, as temperature drops enough to permit these compounds to form from individual atoms combining through chemical reactions. The gas remains too hot for any material to condense into liquid droplets or solid particles yet, with everything existing in vapor phase. But the molecular species present begin to reflect the diversity of elements in the planet's composition. The cloud deck itself marks a crucial boundary in atmospheric structure, defining the altitude where temperature and pressure permit the first condensation of solid particles from vapor, specifically corundum crystals condensing from aluminum oxide gas, as explored in earlier parts. This layer sits at the altitude where temperature crosses the condensation point for aluminum oxide under the local pressure conditions, creating the visible clouds that dominate the planet's appearance from space. The exact altitude varies between dayside and nightside, and with latitude as temperature patterns shift, but typically sits around 200 to 300 kilometers above the reference level, where pressure reaches 1 bar, the pressure of Earth's sea level atmosphere. Below the cloud deck, the atmosphere becomes opaque to visible light, and even to most infrared radiation, as increasing density and the presence of suspended particles block photons from penetrating deeper, creating a region where direct observation becomes impossible, and where our knowledge relies on theoretical modeling and indirect inference. The pressure increases rapidly, with depth in this region roughly doubling every 10 kilometers of descent, creating crushing compression that would destroy any probe attempting to descend below a few hundred kilometers depth. Temperature also increases with depth. Despite the lack of direct stellar heating, the compression of gas under its own weight, generating heat through the same process that warms Earth's atmosphere, and the greenhouse effect from absorbing molecules trapping infrared radiation prevents this heat from escaping upward. The temperature inversion, where temperature increases rather than decreases with decreasing altitude, characterizes most of HAT-P-7b's lower atmosphere, creating a stable stratification that inhibits vertical mixing and separates the deeper atmosphere from the upper layers. This stability, opposite to the unstable convection-prone structure of Earth's troposphere, where temperature decreases with height, prevents the vigorous overturning that would mix atmospheric layers, and creates a more layered structure where different altitude bands maintain distinct chemical compositions and temperature profiles. The day side shows less stable structure than the night side because the intense heating creates enough buoyancy to drive some convection despite the temperature inversion. But even on the day side, the atmosphere remains more stratified than Earth's weather-generating troposphere. Several hundred kilometers below the cloud deck, pressure reaches levels measured in hundreds or thousands of atmospheres, far exceeding anything found in Earth's atmosphere and approaching the pressure found kilometers beneath Earth's oceans. At these pressures, the behavior of gas begins to change as molecules pack closely enough that their mutual interactions become significant compared to their kinetic energy, pushing the atmosphere toward a supercritical fluid state, where the distinction between gas and liquid blurs. Temperature at these depths might reach 4,000 degrees or higher, maintained by compression heating and greenhouse trapping, creating conditions where many compounds that are solid rocks on Earth exist as high-pressure gases or supercritical fluids. The transition to the planetary interior likely occurs gradually, rather than at a sharp boundary, with the atmosphere becoming progressively denser and more liquid-like with increasing depth, until at some point we would recognize the material as more liquid than gas, though no clear surface exists where this transition completes. The interior structure of HAT-P-7b likely resembles Jupiter's interior in broad strokes, with a hydrogen-helium envelope surrounding a core of heavier elements. including rock and metal. Though the extreme heating from the nearby star affects the outer layers significantly compared to Jupiter's cooler envelope. The core, if it exists as a distinct entity, sits perhaps 10 or 20,000 kilometers below the cloud tops, buried under layers of increasingly dense fluid. The scale height, the vertical distance over which pressure changes by a factor of E, about 2.7, characterizes how rapidly atmospheric properties change with altitude and provides a measure of the atmosphere's thickness. HAT-P-7b's scale height in the observable atmosphere measures several hundred kilometers, much larger than Earth's 7-kilometer scale height, reflecting the higher temperature and lower average molecular mass of the gas. This large-scale height means the atmosphere extends further vertically relative to the planet's size compared to Earth's atmosphere, creating a thick, fuzzy boundary between planet and space, rather than the sharp transition Earth demonstrates. The chemical layering within the atmosphere creates zones where different materials can exist in condensed form, with aluminum oxide condensing highest where temperature first drops below its condensation point. Other materials condensing deeper where temperature drops further, and some refractory compounds possibly condensing at great depth where pressure becomes extremely high despite continued high temperature. The vertical sequence of cloud layers, predicted by atmospheric models, shows aluminum oxide clouds highest, followed by layers of titanium oxide, calcium aluminum oxide, and possibly iron silicate clouds deeper still, each layer forming where its characteristic condensation temperature matches the local atmospheric temperature. This layered structure, though much of it remains hidden from direct observation, creates a complex vertical arrangement of different compositions and phases. The dynamics in the lower atmosphere, below the altitude where our observations reach, remain largely mysterious because we cannot see through the opaque upper layers to observe the conditions beneath. Theoretical models suggest continued powerful winds driven by the day-night temperature difference, but whether the flow patterns resemble the upper atmosphere winds or take different forms at high pressure remains uncertain. The interaction between circulation and the chemical layering, the possibility of condensational heating releasing energy as vapor condenses, and the complex radiative effects in a multi-layer cloud system all create complications that challenge atmospheric models and leave significant uncertainties in our understanding of conditions deep in HAT-P-7b's atmosphere. And throughout this vertical structure, from the near vacuum of the exosphere to the crushing high-pressure depths thousands of kilometers down, the temperature and composition create the environment that permits corundum clouds at specific altitudes while preventing them elsewhere, that drives circulation through temperature differences between layers and between hemispheres, that determines what light reaches the cloud deck and what chemistry can occur at each level. The layered architecture, forming the stage on which the gemstone rain performs its endless cycle of condensation and evaporation across the alien sky. Understanding what HAT-P-7b is made of, the fundamental materials that compose this massive world, from its cloud tops to its core, reveals why the exotic weather occurs and why this planet exists in its current form with its particular characteristics. The planet belongs to a class called hot Jupiters, gas giant planets, similar in composition to Jupiter and Saturn, but orbiting extremely close to their parent stars, receiving intense stellar radiation that heats them to temperatures gas giants in our outer solar system, never approach. The composition reflects this gas giant nature, with the bulk of the planet's mass consisting of the same hydrogen and helium that dominate the Sun and most stars. These lightest elements comprising perhaps 90% or more of the total mass. The hydrogen exists primarily in molecular form, H2, in the cooler outer atmospheric layers where temperature permits two hydrogen atoms to bond together. Though at the extreme surface temperatures, individual hydrogen atoms also exist in significant concentrations where thermal energy breaks apart some molecules. Deeper in the atmosphere, where pressure increases to thousands or millions of times Earth's atmospheric pressure, hydrogen undergoes a phase transition to metallic hydrogen, a state where the molecules break apart entirely and electrons move freely between nuclei, creating an electrically conductive fluid that behaves like a liquid metal, despite being composed of the simplest and lightest element. This metallic hydrogen likely composes the bulk of HAT-P-7b's interior, a vast sea of strange matter extending from deep in the atmosphere to the planetary core. Helium, the second most abundant element in HAT-P-7b's composition, makes up perhaps 10 to 25% of the total mass, depending on how much has settled toward the core during the planet's history. A process called helium rain, where helium droplets separate from the hydrogen-helium mixture and fall inward under gravity. Helium remains as individual atoms at all temperatures and pressures relevant to HAT-P-7b, never forming molecules like hydrogen does. Behaving as an inert gas that mixes with hydrogen throughout most of the planet, but potentially separating into distinct layers in the deep interior where immiscibility might occur. The helium contributes to atmospheric pressure and mass, but participates in chemistry only minimally, serving primarily as a diluent that affects the average molecular mass and thermodynamic properties of the atmospheric mixture. The remaining few percent of the planet's mass, though small in percentage terms, amounts to several Earth masses worth of elements heavier than helium. Astronomers call these collectively metals, regardless of their actual chemical nature, using the term to mean anything other than hydrogen and helium. This heavy element fraction includes the familiar elements from Earth's periodic table: carbon, nitrogen, oxygen, silicon, magnesium, aluminum, iron, titanium, and dozens of others, each present in concentrations that reflect the primordial composition of the gas and dust from which the planet formed billions of years ago. These heavy elements, despite being trace constituents by mass, create all the interesting chemistry and weather we observe, forming the compounds that condense into clouds and participate in the complex reactions occurring throughout the atmosphere. Oxygen, the most abundant heavy element, exists primarily combined with hydrogen as water vapor, H2O, in cooler regions of the atmosphere, and as separate atoms or combined with metals as metal oxides in hotter regions, where water molecules dissociate. The water vapor concentration remains uncertain because observations cannot penetrate to the atmospheric levels, where water would condense if it exists as a major component. But models suggest water could contribute significantly to the deeper atmosphere composition if the planet's heavy element enrichment includes substantial oxygen. The metal oxides, including aluminum oxide, the corundum creating gemstone clouds. Titanium oxide, vanadium oxide, silicon oxide, and iron oxide all form from oxygen combining with various metals. These compounds dominating the observable chemistry in the hot upper atmosphere where they exist as vapor. Carbon exists primarily as carbon monoxide, CO, and carbon dioxide, CO2, in most atmospheric models, with methane, CH4, likely dissociated by the high temperatures in the observable atmosphere, though potentially stable in cooler, deeper layers. The carbon chemistry becomes important for understanding the planet's thermal structure and atmospheric opacity, as carbon-bearing molecules absorb infrared radiation and affect heat transport through the atmosphere, though the concentrations remain poorly constrained by current observations. Future spectroscopic studies might detect specific carbon compounds and measure their abundances, providing constraints on the total carbon content and the chemical equilibrium that determines which carbon-bearing molecules dominate under HAT-P-7b's conditions. Aluminum, though a relatively minor constituent, accounting for perhaps tens to hundreds of parts per million of the total atmospheric mass, creates the most visually striking weather feature through the corundum clouds we explored in early parts. The aluminum combines with oxygen to form aluminum oxide molecules, AlO and Al2O3, in the hot upper atmosphere. These molecules condensing into solid corundum particles when temperature drops below the condensation point, around 2,500 degrees Celsius. The total mass of aluminum cycling through the cloud layer represents perhaps millions of tons of material. A number that sounds large, but amounts to only a tiny fraction of the planet's total atmospheric mass, demonstrating how even trace constituents can create prominent observable features. Titanium oxide deserves particular mention among the heavy element compounds because it strongly absorbs visible and near-infrared radiation, creating a temperature inversion in the upper atmosphere by trapping stellar energy and preventing it from penetrating to deeper layers. The titanium oxide molecules, formed from titanium and oxygen atoms combining in the hot gas, exist exclusively in vapor phase, at the temperatures where they occur most abundantly, never condensing into clouds in the observable atmosphere, though models suggest titanium oxide clouds might form in deeper, cooler layers if titanium abundance permits. The absorption properties of titanium oxide make it detectable through spectroscopic observations, allowing astronomers to confirm its presence in HAT-P-7b's atmosphere and estimate its concentration. The silicon, magnesium, and iron content likely manifests primarily in the deep atmosphere, where lower temperatures might permit silicate and iron compounds to condense, though current observations cannot confirm this directly because visible and infrared light cannot penetrate to these depths. Earth's rocky composition comes primarily from silicate minerals, silicon and oxygen combined with various metals, and metallic iron, so the silicon, magnesium, and iron in HAT-P-7b's atmosphere potentially creates clouds or rain of molten rock and liquid iron at depths where temperature drops below their condensation points, while pressure remains high. These deep layers, if they exist, would create weather even more exotic than the corundum rain we observe higher up, with droplets of liquid rock falling through thick gas toward the planetary interior. The overall metallicity of HAT-P-7b, the total heavy element concentration compared to the hydrogen and helium, appears enhanced relative to the star it orbits, suggesting the planet incorporated more rock and ice during formation than a simple gravitational collapse of star composition gas would produce. This enhancement is common in gas giant planets, as the planetary formation process involves building a solid core through accumulation of rocky and icy planetesimals before the core becomes massive enough to gravitationally attract the huge envelope of hydrogen and helium that creates the gas giant. The enhanced metallicity affects atmospheric properties, including density, opacity to radiation, and cloud composition, creating differences from pure hydrogen-helium atmospheres that affect observable characteristics. The core, if distinct core exists at the planet's center, likely consists of rock, silicate minerals, and metal, primarily iron, compressed to extraordinary densities under the weight of the overlying material. Though the exact core composition, and even whether a discrete core persists, rather than dissolving into the metallic hydrogen envelope, remains uncertain. The core mass estimates range from 10 to perhaps 50 Earth masses, depending on assumptions about the interior structure and the degree of heavy element enrichment, with higher estimates requiring that most of the planet's heavy elements concentrated in the core, rather than mixing throughout the envelope. The core temperature might reach 10 to 20,000 degrees, maintained by the primordial heat from formation and possibly supplemented by tidal heating from the star's gravitational influence. The radius of HAT-P-7b, about 1.4 times Jupiter's radius, appears larger than Jupiter's, despite having only about 1.8 times Jupiter's mass, meaning the planet is substantially puffed up or bloated compared to Jupiter's more compact form. This inflation results from the intense stellar heating, which deposits enormous amounts of energy in the upper atmosphere and causes it to expand outward against gravity, creating a lower average density than cooler gas giants demonstrate. The heating prevents the planet from contracting as much as it would if orbiting farther from its star, maintaining a radius that makes the mean density only about 0.42 grams per cubic centimeter, less than half water's density, and meaning this massive planet would float if immersed in a sufficiently large ocean. The mass measurement comes from observing the planet's gravitational effect on its star, the mutual orbit causing the star to wobble slightly as planet and star orbit their common center of mass. Though for HAT-P-7b, the primary detection method used transits, measuring the dimming of starlight as the planet passes in front of the star, as seen from Earth. The radius measurement also comes from transits, specifically from measuring what percentage of the star's light the planet blocks during the transit. Larger planets blocking more light and creating deeper dimming. The combination of mass and radius allows calculating average density and inferring internal structure through comparison with theoretical models of how gas behaves under different temperature and pressure conditions. The planet is slowly evaporating under the intense stellar radiation, losing atmospheric mass to space, as energetic photons give hydrogen atoms enough energy to escape the planet's gravity, a process called hydrodynamic escape, where the uppermost atmospheric layers flow outward into space. The escape rate likely measures tens of millions to billions of kilograms per second, a number that sounds enormous, but represents only a tiny fraction of the planet's total mass when extended over billions of years. The escaping material forms an extended envelope around the planet and streams away in the direction opposite the star, creating a comet-like tail of planetary atmosphere, though far less dramatic than a comet's tail, and detectable only through specialized observations of specific ultraviolet absorption lines. And so this planet, composed of the same elements that form stars and rocky worlds, but arranged differently, massive enough to hold thick hydrogen-helium envelope, yet close enough to its star to be heated to extremes, enriched in heavy elements that create exotic chemistry, yet dominated by the simplest elements from the universe's initial moments, represents nature's ability to create diversity from the same basic building blocks, the same periodic table creating both Earth's temperate, life-bearing surface and HAT-P-7b's gemstone rain atmosphere, through different combinations and conditions and histories, all of it following from fundamental physics and chemistry, operating on the raw materials left over from the galaxy's formation. The star that creates the conditions defining HAT-P-7b's environment, providing the intense heat that maintains extreme temperatures and drives powerful atmospheric circulation, orbits about 1,040 light-years from Earth in the constellation Cygnus the Swan, one point among the countless stars visible to telescopes but distinguishable from most by the massive planet circling it at a distance, that brings the two bodies into an intimate gravitational relationship. HAT-P-7, the star's designation in the Hungarian Automated Telescope Network catalogue where it was discovered, shines with a white light that indicates higher surface temperature than our Sun, classified as an F-type main sequence star according to the spectroscopic classification system astronomers use to categorize stellar temperatures and compositions. The F classification places it between the yellow G-type stars like our Sun and the hotter blue-white A-type stars, creating a stellar environment substantially more energetic than Earth experiences. The surface temperature of HAT-P-7 reaches approximately 6,350 degrees Kelvin, compared to the Sun's 5,778 degrees Kelvin. The 570-degree difference translating to noticeably hotter and brighter emissions across all wavelengths. The higher temperature shifts the star's peak emission towards shorter wavelengths in the blue part of the visible spectrum, creating the white appearance that characterizes F-type stars compared to the yellower tint of G-type stars like the Sun. The total luminosity, the amount of energy the star emits per unit time across all wavelengths, measures about 4 times the Sun's luminosity, meaning HAT-P-7 puts out approximately 4 times as much total power, despite being only moderately larger than the Sun in physical size. The star's radius measures approximately 1.5 times the Sun's radius, making it about 50% larger in linear dimension, and therefore occupying about 3.4 times the volume. Though the relationship between luminosity and size is not straightforward because temperature affects emission rate more strongly than size does through the Stefan-Boltzmann law. The mass of HAT-P-7 reaches about 1.5 solar masses, placing it in the range where stars burn hydrogen into helium in their cores for several billion years before exhausting their fuel and evolving off the main sequence. Though less massive than stars that end their lives as supernovae, and substantially more massive than the smallest red dwarf stars that will burn for trillions of years. The age estimates place HAT-P-7 at approximately 2.2 billion years old. Younger than the Sun's 4.6 billion years, but old enough that the planetary system has had time to evolve and settle into stable configurations. The orbital distance between HAT-P-7b and its star, 0.0379 astronomical units, or about 5.7 million kilometers, creates conditions unlike anywhere in our solar system, closer than Mercury's average distance from the Sun by a factor of more than 10. At this distance, the planet completes one orbit every 2.2 Earth days, racing around the star at speeds exceeding 200 kilometers per second. The orbital velocity, determined by the balance between the star's gravitational pull inward and the planet's inertia carrying it forward. The short orbital period means that HAT-P-7b experiences hundreds of years during a single human lifetime, though the distinction between years and days becomes meaningless for a tidally locked planet where the same hemisphere always faces the star. The tidal locking, the synchronization between the planet's rotation period and its orbital period that keeps one hemisphere perpetually sunlit and the other perpetually dark, results from tidal forces exerted by the star's gravity, acting on the slightly non-spherical shape of the planet. The gravitational force varies with distance, being stronger on the side of the planet closer to the star and weaker on the far side, creating a stretching force that raises tidal bulges in the planet's atmosphere and possibly its interior. When the planet rotates faster than it orbits, these bulges get carried ahead of the planet-star line by rotation, and the star's gravity pulls on the offset bulges to create a torque that slows the rotation. A process called tidal braking that continues until rotation and orbit synchronize. The time required for tidal locking depends on the orbital distance, the planet's mass and size, and its internal rigidity, with closer planets locking faster due to stronger tidal forces. HAT-P-7b likely locked very early in its history, possibly within a few million years of arriving at its current orbital distance, ensuring that the planet has maintained its current orientation for most of its existence. The synchronization remains stable indefinitely, barring major disturbances, because the tidal forces that created it continue to act, correcting any deviations from perfect lock through the same torque mechanism. The result creates the permanent day and night hemispheres that define the planet's climate and atmospheric circulation. The stellar radiation reaching HAT-P-7b's upper atmosphere carries intensity far exceeding what Earth receives. The combination of the star's higher luminosity and the close orbital distance creating an irradiance about 800 times Earth's solar constant. The inverse square law governing radiation intensity means that halving the distance from a light source quadruples the intensity. So HAT-P-7b's position at 1/10 Mercury's orbital distance creates illumination 100 times more intense than Mercury receives. And HAT-P-7's higher luminosity multiplies this by another factor of 4. This intense radiation drives the extreme temperatures we explored earlier, depositing energy faster than the atmosphere can radiate it away and maintaining the furnace conditions that characterize the day side. The radiation spectrum differs from the Sun's, shifted toward shorter wavelengths as expected from the higher surface temperature, with proportionally more ultraviolet and blue light, and proportionally less red and infrared light compared to the sun's spectrum. This shift affects how atmospheric gases absorb the incoming energy. As different molecules absorb different wavelengths preferentially, creating a different pattern of atmospheric heating than would occur under solar radiation. The strong ultraviolet component breaks apart molecules efficiently, dissociating compounds that would remain stable under less energetic radiation and creating a chemically reducing environment where simple molecules and individual atoms dominate over complex compounds. The stellar wind, the stream of charged particles flowing outward from the star's corona, reaches HAT-P-7b with intensity far exceeding the solar wind at Earth's distance. The close proximity, creating impacts measured in thousands of particles per square centimeter per second, compared to the few particles per square centimeter per second that reach Earth. The stellar wind erodes the planet's atmosphere slowly over time, stripping away the outermost layers, particularly on the day side, where the magnetic field, if any, provides less protection. The erosion rate, though small compared to the planet's total atmospheric mass, accumulates over billions of years and contributes to the atmospheric escape that slowly reduces the planet's size. Though HAT-P-7b's substantial mass means the escape does not threaten to strip the atmosphere entirely, the gravitational relationship between star and planet creates mutual tidal effects, with the planet raising small tides in the star, just as the star raises large tides in the planet, though the star's much greater mass means the effect on the star remains minimal. The tidal interaction transfers angular momentum from the planet's orbit to the star's rotation very slowly, causing the orbit to gradually decay over hundreds of millions to billions of years. Though the timescales involved exceed the remaining main sequence lifetime of the star, the eventual fate likely involves the planet spiraling inward as orbital energy dissipates through tidal heating, potentially leading to the planet's destruction as it approaches the stellar surface, though this outcome remains billions of years in the future. The star's location in our galaxy, about 1,040 light-years from Earth, places it in the galactic disk among the population of younger stars that orbit the galactic center in roughly circular paths. The Cygnus constellation, where HAT-P-7 appears in Earth's sky, represents a direction toward the galactic plane, looking through the disk's thickness toward the opposite side of our spiral arm. The distance measurement, determined through multiple methods, including parallax and stellar modeling, carries uncertainties of several percent, but establishes that light leaving HAT-P-7 now left the star around the year 985 in Earth's calendar, meaning we observe the star and its planet as they existed more than 1,000 years ago, when Earth was in its medieval period. The star likely formed from the gravitational collapse of a dense region in a molecular cloud, the same process that creates all stars. With the planet forming from the disk of gas and dust that surrounded the young star during its first few million years of existence, the planetary formation likely occurred farther from the star, where cooler temperatures permitted ice to condense, and where the young star's intense radiation did not prevent gas giant formation, with the planet migrating inward to its current position through gravitational interactions with other planets, or with the disk material itself. This migration transformed the planet from a cold Jupiter analog into the scorched hot Jupiter we observe today. the journey inward redefining everything about the planet's climate and appearance. And so the relationship between HAT-P-7 and HAT-P-7b, star and planet locked in gravitational dance, creates the environment where gemstone rain falls and supersonic winds blow, the stellar radiation providing energy, while the orbital configuration creates the temperature differences and tidal effects that shape atmospheric behavior, the star's brightness and spectrum determining what chemistry occurs and what molecules can survive in the hot upper layers where we observe the corundum clouds shimmering in the starlight, completing the causal chain from stellar properties to exotic weather across millions of kilometers of otherwise empty space. The current configuration of HAT-P-7b, orbiting incredibly close to its star, receiving intense radiation that creates the extreme heat and drives the exotic weather we observe, represents not the planet's original state, but the outcome of a long migration inward from more distant reaches of the planetary system, a journey that transformed it from a likely cold gas giant, similar to Jupiter or Saturn, into the scorched world it has become. Understanding this migration, the processes that moved a massive planet across astronomical unit scales of distance, and the changes that occurred during the journey, reveals how planetary systems evolve and how the diversity of exoplanet configurations we observe came to exist. The story begins billions of years ago when HAT-P-7 was a young star surrounded by a disk of gas and dust from which planets would form. The planet likely formed in the outer reaches of this protoplanetary disk, at distances of several astronomical units from the young star, where temperatures dropped low enough for water, ice, and other volatiles to condense, creating the reservoir of solid material needed to build a massive core capable of gravitationally capturing the huge hydrogen-helium envelope that characterizes gas giants. This region beyond the frost line, the distance from the star where temperature permits ice formation, provided abundant solid material because water ice greatly increases the total solid mass available compared to just rock and metal, allowing rapid growth of planetary cores through collisions and accretion. The core of what would become HAT-P-7b accumulated mass through this process, growing from kilometer-sized planetesimals to a body of perhaps 10 Earth masses over a few million years. Once the core reached sufficient mass, about 10 Earth masses, representing a threshold where the gravitational binding energy exceeds the thermal energy of surrounding gas, it began rapidly accreting hydrogen and helium from the surrounding disk, the light gases falling onto the core and building up the massive envelope. This runaway gas accretion phase proceeded quickly on geological timescales, adding the bulk of the planet's current mass within perhaps 100,000 to a million years, creating a gas giant similar in composition and structure to Jupiter. The planet at this stage orbited several astronomical units from the star, well beyond the habitable zone, experiencing conditions cold enough that methane, water, and ammonia all existed as solid ices rather than gases. The migration inward began through gravitational interactions between the planet and the disk of gas and dust that still surrounded the young star, a process called Type II migration that occurs when a planet becomes massive enough to clear a gap in the disk through its gravitational influence. The planet orbiting through the disk exerts torques on the gas, pushing material outward ahead of its orbit and pulling material inward behind it, creating angular momentum transfer that causes the planet to lose orbital energy and spiral slowly inward toward the star. The rate of migration depends on disk properties, including surface density and viscosity, but typical rates move a Jupiter-mass planet inward by about 1 astronomical unit per 100,000 years, fast enough to dramatically change the orbit over a few million years, but slow enough that the process proceeds smoothly rather than catastrophically. The inward journey transformed the planet's environment gradually, as decreasing distance from the star increased the stellar radiation intensity and raised temperatures at the planet's upper atmosphere. The first changes affected the outermost layers, where low pressure meant that even modest temperature increases could vaporize ices and alter atmospheric composition. Methane, which exists as solid or liquid at the cold temperatures prevailing in the outer system, began to evaporate and exist primarily as gas as the planet moved inward. The increasing ultraviolet radiation also dissociating methane molecules into simpler compounds. Water ice sublimated from surface layers and mixed into the deeper atmosphere, increasing the water vapor content, though likely not reaching the levels where water dominates atmospheric composition. As the planet continued inward past 1 astronomical unit, roughly Earth's distance from its star, the temperatures rose high enough to begin affecting even the deep atmosphere, heating the envelope from outside through intense stellar radiation rather than from internal heat only. The heating caused the atmosphere to expand, the gas pushing outward against gravity as thermal energy increased, beginning the inflation that makes HAT-P-7b larger than Jupiter despite similar mass. The expansion accelerated as the planet approached its current orbital distance, the atmospheric radius growing by tens of thousands of kilometers as temperature soared and pressure at a given altitude decreased correspondingly, transforming the planet's appearance from a compact Jupiter analog to a bloated, hot Jupiter. The final stages of migration brought the planet to its current orbital distance of 0.0379 astronomical units, likely within tens of millions of years of the planet's formation, creating the extreme environment we observe today. The migration might have halted because the protoplanetary disk dissipated, removing the gas that drove the inward spiraling and leaving the planet in whatever orbit it occupied when the disk disappeared. Alternatively, the migration might have continued until tidal interactions between planet and star created enough orbital energy dissipation to balance the continued inward drift from any residual disk material, establishing equilibrium at the current distance. Either way, once established in this close orbit, the planet remained there, tidal locking occurring quickly, and the configuration proving stable over billions of subsequent years. The rotation period changed dramatically during this migration, as tidal forces from the star became stronger with decreasing distance, the synchronization process acting more powerfully as the gravitational gradient across the planet increased. Initially, the planet likely rotated rapidly, like Jupiter does, completing one rotation every 10 hours or less. But tidal braking gradually slowed this rotation through the torque created by tidal bulges misaligned with the planet-star line. The rotation period lengthened steadily until matching the orbital period at 2.2 days, creating the tidal lock that persists today. The transition from rapid rotation to tidal lock altered atmospheric dynamics substantially, ending the strong Coriolis effects that rapid rotation creates, and changing circulation from patterns dominated by rotation to patterns dominated by day-night heating differences. The atmospheric composition evolved throughout the migration as changing temperature altered what compounds could exist in gas versus condensed phases, and as photochemistry under intense ultraviolet radiation created and destroyed various molecules. The metals and silicates that existed as solid particles or condensed layers in the cold outer system vaporized completely as temperature rose during inward migration, transforming from clouds or haze layers into vapor components of the atmosphere. New cloud types formed at the higher temperatures characteristic of the inner orbit, with refractory materials like corundum condensing in place of the volatile ices that characterized clouds in the outer system, creating the gemstone weather we observe, replacing the water ice or methane snow that might have fallen on the planet at its birthplace. The core, if it maintained integrity as a distinct layer rather than dissolving into the envelope, underwent compression as the atmospheric envelope expanded and redistributed mass. The weight of the bloated atmosphere pushing down on deep layers and increasing central pressure. Some models suggest that very massive gas giant cores might dissolve into the surrounding metallic hydrogen under the extreme pressure and temperature conditions in the deep interior, eroding from the outside as core material mixes upward through convection. Though whether this occurs depends on uncertain physics of matter at extreme pressure. If dissolution occurred, the heavy elements from the core now mix throughout the envelope, enriching the atmospheric metallicity and affecting observable properties. The migration likely affected other planets in the system, if any existed, as the inward-moving giant would have gravitationally scattered smaller bodies and potentially ejected additional planets from the system entirely, or disrupted their orbits significantly. No other planets are currently known in the HAT-P-7 system, observations having detected only HAT-P-7b so far. But this absence might result from observational limitations, rather than proving that no other planets exist. The giant's migration might have cleared the inner system of any terrestrial planets that were forming there, disrupting their growth or scattering them outward or into the star, creating a system architecture dominated by the single massive planet close to the star. The alternative to migration scenarios, that the planet formed in situ at its current orbital distance, appears unlikely because temperatures so close to the star would prevent gas giant formation through standard mechanisms, the heat evaporating ices and preventing core growth to the point where runaway gas accretion could begin. In situ formation might occur through unusual mechanisms like gravitational instability, causing the disk to fragment directly into gas clumps. But most planetary formation models favor formation at larger distances, followed by migration for hot Jupiters. The evidence from HAT-P-7b's properties, including its composition and structure, supports the migration scenario, though uncertainties remain about exact mechanisms and timescales. The question of why migration stopped precisely where it did, rather than continuing until the planet spiraled into the star, remains partially answered, with the dissipation of the gas disk representing the most likely explanation for why inward drift ceased. If migration halted because of disk dissipation, the timing was fortunate in that the planet survived rather than being consumed, establishing an orbit close enough to create extreme conditions, but far enough to avoid destruction. Alternative scenarios involving resonances with other planets or disk structure features that halt migration at specific distances might also play roles, though detecting such effects requires detailed modeling of the early system evolution. And so HAT-P-7b arrived at its current state through a journey across its planetary system, transformed from cold Jupiter analog to scorched hot Jupiter by migration that carried it from comfort to extremity. From a world where familiar ices might have created conventional weather, to a furnace where gemstones condense from atmospheric vapor. The planet's history written in its current properties and inferred from models that attempt to reconstruct the early solar system evolution from the outcome we observe billions of years later across interstellar distances. The story of how astronomers discovered HAT-P-7b and came to understand its exotic atmosphere, including the gemstone clouds and extreme conditions we have explored, unfolds across more than a decade of increasingly sophisticated observations, beginning with the planet's initial detection and extending through detailed characterization that revealed its remarkable properties. The discovery occurred in 2008 through the Hungarian Automated Telescope Network, called HAT-NET, a coordinated set of small automated telescopes designed specifically to find transiting exoplanets by continuously monitoring thousands of stars and searching for the periodic dimming that occurs when a planet passes in front of its star from our viewing perspective. The HAT telescopes, despite their modest 6-inch apertures, achieved the precision needed to detect Jupiter-sized planets through their distinctive light curves. The detection method, called the transit method, relies on geometric alignment, where Earth, the planet, and the star all lie approximately in the same plane, so that the planet's orbit carries it directly between us and the star during part of each orbit. When this alignment occurs, the planet blocks a small fraction of the star's light, creating a dimming that sensitive measurements can detect, despite typically amounting to only 1 to 2% brightness reduction. HAT-P-7b's transits dim the star by about 0.8%, a subtle drop, but easily measurable with modern photometry, with each transit lasting about 4 hours as the planet crosses the stellar disk at its orbital velocity of 200 kilometers per second. The periodic nature of the dimming, repeating every 2.2 days with consistent depth and duration, provides strong evidence that a planet causes the signal rather than stellar variability or instrumental effects, as only an orbiting body produces such regular periodic signatures. The analysis of multiple transits observed over weeks and months allowed the team to determine the orbital period precisely, measure the transit depth to calculate the planet's radius relative to the star, and derive other geometric parameters, including the orbital inclination and the impact parameter, describing how centrally the planet crosses the stellar disk. These measurements from transits alone revealed that HAT-P-7b was a gas giant larger than Jupiter, orbiting a bright star with a period of only days. The follow-up observations required to confirm the planet's existence and measure its mass used a different technique called radial velocity spectroscopy, where astronomers measure the Doppler shift in the star's spectral lines caused by its orbital motion around the center of mass shared with the planet. The planet's gravity pulls on the star, just as the star pulls on the planet, causing the star to wobble slightly in space, moving toward and away from Earth by tens of meters per second as the planet orbits. This motion shifts the star's spectrum toward bluer wavelengths when the star moves toward us, and toward redder wavelengths when moving away, creating a periodic oscillation in spectral line positions that matches the orbital period measured from transits. The combination of transit observations showing the planet's size and radial velocity measurements showing its mass allowed astronomers to calculate HAT-P-7b's density, revealing the bloated nature that characterizes hot Jupiters. The low density confirming the planet consisted primarily of hydrogen and helium rather than heavier materials. The announcement in 2008 generated interest because HAT-P-7b orbited a relatively bright star, making it amenable to detailed follow-up studies. And because the short orbital period and large planetary radius created favorable conditions for atmospheric characterization through techniques that probe the planet's composition and structure. The Kepler Space Telescope, launched in March 2009 specifically to find transiting exoplanets and determine how common Earth-sized planets are in the galaxy, selected HAT-P-7 as one of the roughly 150,000 stars it would monitor continuously for years, providing an opportunity to study HAT-P-7b with unprecedented precision and overextended timescales. Kepler's observations, beginning in May 2009, measured the star's brightness with precision of about 20 parts per million over time intervals of 30 minutes, far exceeding the precision of ground-based observations and allowing detection of subtle variations in the planetary signal that revealed atmospheric properties. The key breakthrough came from analyzing not just the transits themselves, but the entire light curve, showing how the star plus planet system brightness varies throughout the orbit, a technique called phase curve photometry. As HAT-P-7b orbits, different portions of the planet's atmosphere become visible from Earth, with the day side appearing near maximum brightness when the planet lies on the opposite side of the star from Earth and disappearing during transit, while the night side becomes visible when the planet passes behind the star in an event called secondary eclipse. The changing visibility of different atmospheric regions creates a sinusoidal variation in total brightness that Kepler detected despite the tiny amplitude, revealing information about temperature distribution and cloud patterns. The analysis of Kepler phase curves showed that the brightest point on HAT-P-7b did not coincide exactly with the center of the day side where stellar heating is most intense, but instead appeared offset toward the evening terminator, the boundary between day and night on the planet's trailing hemisphere. This offset indicated that powerful winds carried heat from the day side toward the night side, moving the hottest region downstream from the point of maximum heating, creating the asymmetric temperature distribution that observations detected. The offset measurement provided direct evidence for the supersonic winds we explored earlier, confirming that atmospheric circulation dramatically redistributes heat and creates weather patterns that affect observable properties. The atmospheric composition came into focus through spectroscopic observations made during transits and secondary eclipses. Techniques that measure what wavelengths of starlight the atmosphere absorbs as it passes in front of the star, or what wavelengths the planet emits when its day side faces Earth. These observations, technically challenging because they require detecting tiny spectral signatures from a planet much dimmer than its star. Gradually revealed evidence for various compounds, including water vapor, carbon monoxide, and, critically for our story, aluminum oxide and titanium oxide, creating the high-temperature clouds and hazes. The Corundum detection came from identifying absorption features at specific infrared wavelengths, characteristic of aluminum oxide, confirming that the material we discussed forming gemstone clouds actually exists in the atmosphere. The human element behind these discoveries involves teams of astronomers working over years to collect data, develop analysis techniques, and publish results that each add small pieces to the complete picture. The initial HAT team included several dozen researchers operating the automated telescopes and analyzing their data streams, identifying candidate planets from thousands of stellar light curves, and coordinating follow-up observations to confirm detections. The Kepler team involved hundreds of scientists and engineers designing the spacecraft, operating it through its multi-year mission, processing the enormous datasets it produced, and analyzing specific targets, including HAT-P-7b, to extract atmospheric properties. The publications describing HAT-P-7b's discovery and subsequent characterization span many scientific papers released over more than a decade, each adding details about orbital properties, mass, radius, atmospheric composition, temperature structure, cloud properties, and variability, the full picture emerging gradually, rather than appearing complete in any single observation. The ongoing nature of exoplanet science means new observations continue to refine our understanding. With James Webb Space Telescope observations of HAT-P-7b and similar hot Jupiters planned to measure atmospheric chemistry with unprecedented precision and detect compounds that earlier instruments could not observe. The emotional aspect of discovery, though rarely appearing in formal scientific papers, drives the persistence required to tease these findings from noisy data and limited signals. Researchers described the satisfaction of detecting a planet's transit in data, the excitement when follow-up observations confirm the discovery, the wonder of realizing that photometry reveals atmospheric properties of a world 1,000 light-years distant, and the ongoing fascination with how much we can learn about planets we will never visit through careful analysis of the starlight that reaches us across interstellar space. The HAT-P-7b work exemplifies the combination of technology, methodology, and human dedication that characterizes modern exoplanet science. The challenge of detecting gemstone rain specifically, rather than just confirming aluminum oxide exists in the atmosphere, comes from the difficulty of distinguishing condensed particles from vapor through remote observations, a problem requiring sophisticated modeling of how light scatters from crystals versus absorbing in gas, and how different particle sizes affect spectral signatures. The evidence for corundum clouds, rather than just corundum vapor, comes from theoretical calculations showing temperature and pressure permit condensation at specific altitudes combined with observations, showing light scattering consistent with particles in the atmosphere. The combination building the case that actual crystals exist, rather than just their component molecules. The ongoing monitoring of HAT-P-7b reveals that its atmospheric properties change over time, with brightness variations on timescales of days to months, suggesting that cloud coverage or distribution shifts, possibly due to weather evolution or changing patterns in atmospheric circulation, demonstrating that the planet has dynamic variable atmosphere rather than unchanging static conditions. These variations, though small, create opportunities to study atmospheric dynamics through repeated observations that map how conditions evolve, complementing the snapshot views from individual observations with understanding of temporal changes and cyclical patterns. And so the knowledge we possess of HAT-P-7b, from its basic properties to its atmospheric composition to the exotic weather that creates gemstone rain, emerged through the patient accumulation of observations and careful interpretation of subtle signals in starlight, each measurement adding confidence to our picture of this distant world, and each new capability enabling detection of fainter or more subtle features. The process continuing as technology improves and new questions arise. The planet revealing itself slowly through light that traveled 1,000 years through space to reach the telescopes that capture and analyze it, transforming photons into understanding across the vast distance that prevents direct exploration. Among the growing catalogue of exoplanets discovered and characterized over recent decades, HAT-P-7b represents just one example of extreme worlds that challenge our Earth-centric understanding of what planetary atmospheres can be. And briefly exploring several other planets with exotic precipitation and unusual weather patterns reveals both the diversity nature creates and the context in which HAT-P-7b's gemstone rain sits. These visits remain brief, a gentle tour rather than deep exploration, allowing us to appreciate the variety while maintaining focus on the world where we began. Each stop adding perspective on the strange conditions that occur on planets throughout the galaxy. We begin with WASP-76b, a hot Jupiter slightly more extreme than HAT-P-7b, where the dayside temperature approaches 3,000 degrees Celsius and vaporized iron rains down on the night side. WASP-76b orbits even closer to its star than HAT-P-7b, completing each orbit in just 1.8 days. The tight orbit creating temperatures that vaporize not just corundum, but metallic iron as well, keeping iron in gaseous form on the intensely heated dayside. The powerful winds that circulate the planet, similar in mechanism to HAT-P-7b's circulation, carry iron vapor from the dayside toward the night side, where cooler temperatures permit condensation, creating clouds of liquid iron droplets forming in the cooling gas. These droplets, tiny molten metal spheres, perhaps micrometers to millimeters across, fall through the night-side atmosphere as iron rain, glowing orange-red from their heat despite the surrounding darkness. The spectacle of metal precipitation occurring continuously in the eternal night. The rain likely evaporates before reaching deep atmospheric layers, similar to corundum rain on HAT-P-7b, as falling droplets encounter increasingly hot gas and either boil back to vapor or remain suspended at the altitude where their temperature matches the surrounding air. The cycle repeats endlessly, with iron vapor rising on the day side through convection and stellar heating, flowing to the night side in the upper atmosphere, condensing on the night side into droplets, raining down until evaporation occurs, and cycling back toward the day side to begin again. The discovery of this iron rain came through spectroscopic observations that detected iron absorption lines appearing and disappearing as different parts of the planet rotated into view. Evidence that iron exists in the atmosphere and concentrates in particular regions. The vividness of molten metal falling through alien skies captures imagination while remaining scientifically confirmed through careful measurement and analysis. Moving to another world, HD 189,733b presents conditions equally extreme but manifest in different chemistry, with clouds made of silicate particles creating what astronomers describe as glass rain, driven sideways by winds reaching 5,400 miles per hour. This planet, slightly smaller than Jupiter, orbits a K-type star every 2.2 days, close enough that tidal forces have locked one hemisphere in perpetual day. The temperature on the day side approaches 1,000 degrees Celsius, hot enough to vaporize silicate minerals that exist as rocks on Earth, creating atmospheric vapor that condenses into tiny particles of molten or solid silicate glass on the cooler night side. The extreme wind speeds, among the fastest detected on any planet, create conditions where any rain that forms would fall nearly horizontally rather than vertically. The sideways glass precipitation driven by winds 7 times faster than Earth's most powerful hurricanes. The silicate particles, likely resembling tiny shards of volcanic glass or obsidian, move through the atmosphere at hypersonic speeds, scouring anything they encounter, creating an environment where material erosion would occur at rates impossible in Earth's gentle winds. The planet appears deep blue, invisible light, possibly from the way light scatters through its silicate-laden atmosphere, creating a deceptively beautiful appearance that hides the violent conditions beneath the cloud tops. WASP 121b offers yet another variation, an ultra-hot Jupiter with dayside temperatures exceeding 2,500 degrees Celsius, where metals exist as vapor in the upper atmosphere and condensed liquid deeper down. Observations suggest iron and corundum both condense in this planet's atmosphere, with liquid iron droplets and possibly corundum crystals forming in layers where temperature drops below their respective condensation points. The planet experiences such intense stellar heating that its atmosphere extends far into space, puffed up by thermal expansion, making it one of the largest known planets by radius, despite having only modest mass. The escaping atmosphere, stripped away by stellar radiation, creates a comet-like tail of gas, extending behind the planet as it orbits. HAT-P-7b presents a different spectacle, appearing unusually bright in reflected light due to highly reflective clouds that possibly contain tiny mineral particles, acting like mirrors in the sky. The exact composition remains uncertain, with candidates including magnesium silicate clouds or other mineral aerosols, suspended at altitudes where they efficiently reflect starlight back to space. The high reflectivity, or albedo, makes this planet shine brighter than many hot Jupiters, suggesting that cloud composition and particle size create conditions favorable for light reflection rather than absorption. The brightness variations observed as the planet orbits indicate that cloud coverage changes with atmospheric circulation, creating dynamic weather patterns visible from thousands of light years away through careful photometric monitoring. Each of these worlds demonstrates that the extreme heat generated by orbiting close to bright stars creates atmospheric chemistry impossible in cooler environments, with materials that form solid rocks on Earth existing as vapors, liquids, or clouds on these scorching giants. The commonality among them reveals patterns in how heat and gravity and stellar radiation interact to create weather, while the differences show that each planet's specific temperature, composition, and stellar environment produce unique outcomes. Iron rains on one world, glass flies sideways on another, corundum and iron condense together on a third. Reflective mineral clouds form on a fourth, and on HAT-P-7b, aluminum oxide creates clouds of sapphire and ruby crystals cycling through their own atmospheric patterns. The diversity extends beyond these few examples, with dozens of hot Jupiters discovered and characterized, showing temperatures ranging from 1,000 to 4,000 degrees Celsius, creating a continuum of conditions and chemistries. Some planets show evidence of titanium oxide clouds. Others display vanadium oxide or calcium compounds in their spectra, each element condensing at specific temperatures and creating atmospheric features that astronomers detect through spectroscopy and photometry. The hottest planets may have liquid iron or even molten silicate rock raining through their lower atmospheres, while slightly cooler ones host mineral clouds more exotic than anything Earth produces, yet less extreme than vaporized metals. The ongoing discoveries continue adding to this catalogue of extreme worlds, with each new planet characterized, revealing whether it fits expected patterns or presents novel atmospheric phenomena. The James Webb Space Telescope, operating since mid-2022, brings unprecedented capability for studying exoplanet atmospheres through detailed spectroscopy, revealing molecular compositions, temperature profiles, and cloud properties with precision impossible for earlier instruments. Future observations will likely discover even more exotic precipitation types on planets at different temperatures and stellar distances, expanding our understanding of what atmospheric chemistry can produce under various conditions. The tour through these alien worlds provides context for HAT-P-7b, showing that gemstone rain, while exotic by Earth standards, represents one outcome among many where extreme heat transforms solid materials into atmospheric gases that condense into unusual precipitation. The commonality of tidal locking creates the day-night temperature differences that drive powerful winds on all these planets. Winds that transport vaporized materials from hot regions to cooler regions where condensation occurs. The differences in stellar type, orbital distance, planetary mass, and atmospheric composition create the specific variations that make each world unique despite following similar physical principles. Standing back from the details, the pattern that emerges shows nature exploring every possible combination of conditions that physics and chemistry allow, creating planets that span the full range from frozen ice worlds to these scorching hot giants where rocks vaporize and metals rain from skies. The hot Jupiters represent extreme cases, pushed to high temperatures by proximity to their stars, but they exist on a continuum with cooler gas giants, like our Jupiter and Saturn, that host more familiar weather of hydrogen, helium, methane, and ammonia clouds. Each planet teaches us something about atmospheric processes, about how temperature determines which compounds can exist in which phases, about how winds distribute heat and materials, about how stellar radiation shapes and erodes atmospheres over time. The appreciation for HAT-P-7b deepens through seeing it alongside its exotic cousins, recognizing that while corundum clouds may sound impossible, they represent exactly what we would predict for a planet at that specific temperature and composition. The physics makes sense. The chemistry follows known patterns. The observations confirm what theory predicts. And the result is a planet where aluminum oxide behaves the way water behaves on Earth, cycling between vapor and condensed phases, creating clouds and precipitation, participating in weather patterns driven by heat and wind and gravity. The impossibility fades when we understand the conditions, replaced by the recognition that extreme temperatures create extreme outcomes, but always following the same physical laws that govern gentler atmospheres. Returning our focus to HAT-P-7b after this brief tour, we carry with us the knowledge that this world represents one point in a vast parameter space of possible planets. Neither the most extreme nor the least, but remarkable in its own right for the specific chemistry its conditions create. The gemstone rain continues falling through the atmosphere of HAT-P-7b, regardless of whether we observe it or think about it or compare it to other worlds. The corundum crystals condensing and evaporating in cycles driven by the planet's heat and circulation, creating beauty and strangeness on a world that exists whether we know about it or not. The tour reminds us that the universe contains multitudes, that planetary diversity exceeds what our single solar system shows, and that the galaxy likely harbors millions of worlds, each with its own unique atmospheric conditions and weather patterns, most of them unknown to us, waiting for discovery through future observations and continued exploration. The scientific value of studying HAT-P-7b and worlds like it extends far beyond simple cataloguing of exotic phenomena, reaching into fundamental questions about planetary formation, atmospheric physics, and the diversity of outcomes that nature produces when gravity and chemistry and stellar energy interact. Understanding what this planet teaches us requires recognizing both the specific insights it provides and the broader context it contributes to our evolving comprehension of how planets work and what conditions they can maintain. The knowledge emerges slowly through accumulated observations, theoretical modeling, and careful interpretation of data that arrives as patterns of light after traveling 1,000 years across space. The study of extreme atmospheres like HAT-P-7b's reveals how materials behave under conditions impossible to replicate in Earth laboratories, where temperatures reach thousands of degrees and pressures exceed anything our facilities can sustain for extended periods. The corundum clouds demonstrate that aluminum oxide can exist in vapor form at high temperatures and condense into crystals when cooled, confirming thermodynamic predictions through natural demonstration at planetary scales. The observations of atmospheric composition, wind patterns, and temperature distribution test are models of atmospheric circulation and heat transport, revealing whether our understanding of fluid dynamics and thermodynamics applies correctly to these extreme cases or requires modification. The planet also teaches us about tidal locking and its consequences, showing clearly how permanent day-night differences drive powerful atmospheric circulation when one hemisphere receives constant stellar heating while the other radiates heat to space without receiving new energy. The offset of the hottest region from the point directly beneath the star, detected through careful phase curve observations, demonstrates that winds transport heat faster than the atmosphere can radiate it away, creating a hot spot downstream from the substellar point. This observation confirms theoretical predictions about superrotation and equatorial jet streams on tidally locked planets, validating atmospheric models that can then be applied to other worlds with similar configurations. The study of atmospheric escape, where HAT-P-7b slowly loses gas to space under intense stellar radiation and thermal expansion, reveals processes important for understanding long-term planetary evolution and habitability. Hot Jupiters, like HAT-P-7b, lose atmosphere at rates measurable over human timescales, offering real-time observations of processes that occur more slowly on cooler planets, but remain important for determining which planets retain atmospheres over billions of years. The mechanisms of atmospheric escape, including thermal evaporation, stellar wind interactions, and photochemical dissociation, all operate on HAT-P-7b at enhanced rates, making it a natural laboratory for studying processes relevant to planetary atmospheres throughout the galaxy. The migration history that brought HAT-P-7b to its current close orbit informs our understanding of planetary system formation and evolution, demonstrating that planets do not necessarily remain where they form, but can migrate substantial distances through gravitational interactions. The discovery of hot Jupiters orbiting very close to stars came as a surprise when the first exoplanets were found in the 1990s, challenging theories that assumed planets would remain near their formation locations. The recognition that migration occurs commonly has reshaped models of planetary system formation, leading to better understanding of how planets interact with protoplanetary disks and with each other during the chaotic early periods of system evolution. The technological achievement represented by detecting and characterizing HAT-P-7b deserves recognition as well, as the observations require measuring tiny brightness variations from a star 1,000 light-years away, and interpreting those variations to infer properties of an object 100,000 times fainter than its star. The transit method that revealed the planet's existence depends on precise photometry, detecting a 1% brightness dip lasting a few hours every 2.2 days. A signal easily lost in stellar variability or instrumental noise without careful data processing. The spectroscopic observations that identified atmospheric composition require separating the planet's tiny contribution to the system's spectrum from the overwhelming light of the star, a technical challenge solved through clever observing strategies and sophisticated analysis. The limitations of our knowledge about HAT-P-7b remind us that, while we understand much, vast amounts remain unknown and unknowable with current technology. We infer the atmospheric composition from spectroscopic features, but cannot directly sample the gas to measure abundances precisely or detect trace compounds below our detection thresholds. We calculate temperature from brightness measurements and models, but cannot measure it directly with thermometers distributed through the atmosphere. We detect wind patterns from brightness variations, but cannot observe the three-dimensional flow structure that determines where material moves and how heat transfers. The planet remains distant and inaccessible, except through the information that light carries across space. The questions raised by studying HAT-P-7b extend beyond this single planet to the broader population of hot Jupiters and exoplanets generally, asking how common such planets are, how they affect other planets in their systems, and whether they represent a common outcome of planet formation or an unusual configuration. The statistics emerging from exoplanet surveys suggest that a few percent of Sun-like stars host hot Jupiters, making them relatively common despite their extreme nature, though the reasons why some systems produce hot Jupiters while others do not remain incompletely understood. The presence of a hot Jupiter may affect the formation and survival of smaller rocky planets in the inner system, potentially preventing Earth-like worlds from existing in systems with close-orbiting gas giants, though this influence remains uncertain and debated among researchers. The diversity of hot Jupiters, with each one showing slightly different atmospheric composition, temperature distribution, and wind patterns, depending on stellar type and orbital distance, demonstrates that even within this category of extreme planets, significant variation exists. Some hot Jupiters show strong thermal inversions where upper atmosphere temperatures exceed lower atmosphere temperatures, while others like HAT-P-7b show more conventional temperature profiles decreasing upward. Some display powerful day-night temperature contrasts with minimal heat redistribution, while others transport heat efficiently enough to warm their night sides significantly. The variations teach us which factors determine atmospheric behavior and how sensitive planetary conditions are to differences in stellar radiation, orbital distance, and planetary properties. The future of HAT-P-7b studies includes observations with increasingly sophisticated instruments, particularly the James Webb Space Telescope, which can measure atmospheric composition with unprecedented precision through high-resolution spectroscopy during transits and throughout the orbital phase. These observations will reveal which molecules exist in the atmosphere beyond the corundum already detected, potentially identifying water vapor, carbon monoxide, methane, and other species that inform understanding of atmospheric chemistry and carbon to oxygen ratios. The measurements will also constrain temperature structure more precisely and possibly detect weather patterns through time-variable spectroscopic features that indicate changing cloud coverage or wind-driven circulation variations. The broader scientific context positions HAT-P-7b as one example in the rapidly growing field of exoplanet atmospheric characterization, where planets around other stars transition from simple dots of light to worlds with measurable properties and atmospheric behaviors. The field has progressed from merely detecting exoplanets to characterizing their atmospheres, measuring winds, mapping temperature distributions, and identifying cloud compositions, creating a revolution in planetary science comparable to the initial discovery of exoplanets in the 1990s. HAT-P-7b participates in this revolution as a particularly amenable target for detailed study due to its large size, hot temperature creating strong signals, and the brightness of its host star enabling high-quality observations. The philosophical dimension of studying such alien worlds touches on questions about our place in the universe and the nature of planets more generally, challenging assumptions rooted in our experience of the solar system. The recognition that planets like HAT-P-7b exist, where gemstones form in atmospheres and iron rains from skies, expands our concept of what planets can be beyond the familiar rocky terrestrial worlds and cold gas giants we knew before exoplanet discoveries began. The universe demonstrates creativity in assembling matter into planetary systems that exceeds what our limited sample of 8 planets suggested was possible, revealing that Earth-like conditions represent one outcome among countless variations nature produces. The humility this knowledge induces comes from recognizing that our solar system, long considered the template for understanding planetary systems, represents merely one configuration among vast diversity, and perhaps an unusual one at that, with its lack of hot Jupiters and super-Earths and its relatively circular, coplanar orbits. The exoplanet population reveals systems very different from ours, with giant planets orbiting closer than Mercury, multiple planets packed into tight orbits, highly eccentric orbits, creating extreme seasonal variations, and configurations our solar system simply does not demonstrate. HAT-P-7b reminds us that planetary diversity exceeds our expectations, and that nature fills every niche that physics permits with some kind of world. The wonder that studying HAT-P-7b inspires stems from the combination of extreme conditions and remarkable beauty. The recognition that corundum crystals form spontaneously in the atmosphere of a world heated to temperatures that vaporize rock, creating clouds that shimmer with metallic luster, and rain that falls in particles of sapphire and ruby. The extremity makes the planet fascinating scientifically, but the beauty adds an aesthetic dimension that makes the science emotionally resonant, connecting intellectual understanding with a sense of awe at nature's capacity to create remarkable phenomena from basic physical laws. The gemstone rain exists not because of intention or design, but because chemistry and thermodynamics operate predictably, creating beauty as a byproduct of physical processes. The ongoing nature of the planet's weather, the fact that these processes continue right now, regardless of whether we observe them, creates connection across the 1,000 light years separating us from HAT-P-7b. At this moment, as we consider the planet's characteristics, the Corundum clouds drift through its atmosphere, carried by supersonic winds, crystals condensing and evaporating in endless cycles. The weather happens continuously, day and night blurring into one another on the permanently illuminated day side, while the night side remains in eternal darkness, the boundary between them swept by winds that never cease. The planet orbits its star as it has for billions of years, completing another revolution every 2.2 days, the pattern repeating without variation or pause. The timescales involved dwarf human experience, as HAT-P-7b has likely existed for over 2 billion years and will continue for billions more until its star evolves and changes the system's dynamics. The Corundum rain has fallen for longer than complex life has existed on Earth. The atmospheric circulation has transported heat from day to night through more cycles than we could count. And the tidal lock has held the same face toward the star through countless orbits. The planet exists on geological and astronomical timescales where individual human lives become meaningless flickers. Yet we can study and understand it through observations made over just a few years. Our brief attention sufficient to reveal processes operating across eons. The accessibility of knowledge about such a distant world represents one of science's greatest achievements. As we extend our understanding across interstellar distances, using only the information carried by light. The photons that left HAT-P-7b 1,000 years ago, when human civilization was far different, and our knowledge of the cosmos vastly more limited, arrive now at our telescopes, carrying data about temperatures and winds and atmospheric composition encoded in wavelengths and timing. We decode this information through careful measurement and theoretical interpretation, reconstructing a picture of a world we cannot visit from the subtle signals embedded in starlight, transforming dots of light into understood planets with mapped weather and measured properties. And so, the knowledge accumulates, observation by observation, measurement by measurement, each one adding detail to our understanding of HAT-P-7b and contributing to broader comprehension of planetary atmospheres and exotic weather and the diversity of worlds the universe produces. The planet teaches us about extremes, about what happens when planets orbit too close to stars, about how chemistry behaves at temperatures that vaporize stone, about winds that blow at hypersonic speeds, about clouds that form from materials that are solid rocks on Earth. Each lesson expands our knowledge and reminds us that the cosmos contains wonders we are only beginning to discover. Planets like HAT-P-7b, where the impossible becomes routine and where beauty emerges from extremity. We return now to where we began, floating among the Corundum clouds in the upper atmosphere of HAT-P-7b, but we arrive with understanding that transforms observation into comprehension. The shimmering blue clouds that surround us no longer appear merely beautiful, but reveal themselves as the inevitable consequence of temperature and pressure and chemical composition. Aluminum oxide reaching its condensation point in this particular layer of atmosphere, where heat and cold balance precisely. The crystals forming around us represent not magic, but thermodynamics, molecules of aluminum and oxygen bonding into the crystal structure we know on Earth as corundum, the same mineral that creates rubies when chromium traces tint it red, and sapphires when iron and titanium create blue. The fall of these crystals, the gentle drift downward through increasingly hot atmospheric layers, follows paths determined by gravity and drag and thermal currents, each crystal a tiny test particle, demonstrating how matter moves through this exotic environment. We understand now that the crystals will not reach any surface, because no surface exists, only atmosphere transitioning gradually to liquid and possibly solid deep in the interior. The distinction between atmosphere and planet blurred by extreme pressure. The crystals fall until heat vaporizes them back into gas, the atoms separating and rising again on thermal currents, completing cycles that have repeated billions of times and will continue as long as the planet exists. The context enriches the experience. As we now recognize the star HAT-P-7 hanging in the sky beyond these clouds, its white light providing the energy that drives all the weather we observe, heating the atmosphere to temperatures that vaporize corundum and create the conditions allowing these exotic clouds to form. The orbital configuration makes sense now. The planet's position just 4 million miles from its star, creating the extreme heat that characterizes this world. The tidal lock keeping one hemisphere permanently facing the stellar furnace, while the other faces eternal night. The supersonic winds we discussed carry these clouds we float among, transporting them from day to night and back again in circulation patterns, powered by temperature differences between hemispheres. The migration that brought HAT-P-7b to this location, the billion-year journey inward from wherever it formed in the cooler outer reaches of its stellar system, resulted in the conditions we observe, transforming what was likely a cold Jupiter similar to our own into this scorching world where stone exists as vapor and atmosphere. The planet survived the migration and now exists in a stable configuration that will persist for the remaining lifetime of its star. The orbital mechanics and tidal forces balanced into an equilibrium that requires no further major changes. We float in the atmosphere of a world that has found its place in the cosmos and will remain there through timescales that dwarf human civilization's entire existence. The other planets we briefly visited, the worlds where iron reigns and glass blows sideways in hypersonic winds, exist alongside HAT-P-7b in the catalogue of hot Jupiters, each one demonstrating different outcomes from similar starting points, each one exploring a different corner of the space of possible planetary atmospheres. HAT-P-7b distinguishes itself through the particular beauty of corundum clouds and the scientific accessibility of its atmospheric properties, making it a favorable target for detailed study. The gemstone rain becomes this planet's signature phenomenon, the characteristic that makes it memorable and distinct among the growing population of characterized exoplanets, the detail that captures imagination while exemplifying real atmospheric chemistry operating at extremes. The 1,000 light-years separating us from this world matters less than it might seem. As light crosses that distance, carrying information that allows us to understand conditions we cannot directly experience. The telescope observations that revealed the planet's existence and characterized its properties bridged the spatial gap through electromagnetic radiation, the universal messenger that carries data across cosmic distances at the maximum possible speed. The photons that left HAT-P-7b while human civilization was entering the medieval period on Earth now arrive at our instruments, their wavelengths and timing encoding information about the world they left behind, creating a connection between there and here, mediated by light and decoded by science. The impossibility of visiting HAT-P-7b with current or foreseeable technology does not diminish the reality of the knowledge we possess about it, as the scientific method allows understanding without direct contact through careful observation and logical interpretation. We know the temperature because we measure the thermal radiation. We know the composition because we identify spectroscopic signatures. We know the wind patterns because we track brightness variations that indicate atmospheric motion. The knowledge stands on firm foundations of measurement and physics, even though no human will likely ever travel to this distant system or sample its atmosphere directly. The gemstone clouds drift and flow around us as we observe their motion, controlled by winds we now understand emerge from day-night temperature differences and equatorial jets. Their composition determined by the particular mix of elements the planet contains and the temperature at this altitude. The blue color that dominates comes from trace elements incorporated into the corundum crystal structure. Iron and titanium creating the same blue that makes Earth's sapphires valuable. Though here the color appears in countless tiny crystals floating through the atmosphere, rather than in rare gems mined from the ground. The beauty exists independent of economic value, created by natural processes indifferent to human concepts of worth. The scale of what we observe begins to register more fully. As these clouds extend across regions larger than Earth, the atmospheric currents carrying them operate at planetary scale. And the energy driving the circulation exceeds all human energy production by factors of billions or more. The single planet, HAT-P-7b, contains more material than 1,000 Earths, its atmosphere more massive than our entire planet, its energy budget dwarfing anything in human experience. We float, as observers, in a system operating at scales, where human presence becomes cosmically insignificant. Yet, our minds can comprehend the processes, and our science can measure the properties. Bridging the scale gap through understanding. The time we have spent exploring this world, moving through its atmospheric layers, and learning its properties, comes to a natural conclusion as comprehension reaches completeness within the limits of current knowledge. We have experienced the clouds, followed the rain, understood the heat, mapped the winds, explored the atmospheric structure, analyzed the composition, met the star, learned the history, discovered how we know these things, compared this world to others, and reflected on what it all means. The journey through HAT-P-7b feels complete, not because nothing more could be learned, but because we have touched all the major aspects and built a coherent picture of this world and its place in the cosmos. The clouds surrounding us continue their eternal motion, indifferent to our observation. The crystals forming and falling and evaporating according to physical laws that operated long before we discovered this planet, and will continue long after human civilization has ended. The weather of HAT-P-7b proceeds according to its own rhythms, powered by stellar energy and governed by thermodynamics and fluid dynamics, creating patterns that repeat with each orbit, yet vary in detail as turbulence and chaos introduce endless variation within the overall structure. The Corundum rain falls now, as it has fallen for billions of years, witnessed by no one until recently, yet real and ongoing regardless of observation. The privilege of understanding, of being among the first humans to know that such a world exists, and to comprehend its nature through scientific investigation, comes with responsibility to share the knowledge and inspire wonder at the cosmos's diversity. HAT-P-7b deserves to be known not just as a data point in catalogues, but as a real place with definite properties and remarkable characteristics. A world that expands our conception of planetary possibilities and reminds us that nature's creativity exceeds our imagination. The gemstone rain serves as an accessible entry point to the science, capturing attention through its intrinsic beauty and strangeness, then leading to deeper understanding of atmospheres and chemistry and planetary physics. The completion of our exploration leaves us changed in small ways. Our mental model of the universe expanded to include HAT-P-7b and worlds like it. Our appreciation for planetary diversity deepened through encountering conditions so alien, yet so explicable through physics and chemistry we understand. The knowledge becomes part of how we see the cosmos, contributing to the accumulated understanding that humanity builds generation by generation through patient observation and careful thought. Each person who learns about HAT-P-7b and its gemstone rain adds this knowledge to their worldview, enriching their sense of what exists beyond Earth's familiar conditions. The clouds begin to fade as we prepare to depart this alien atmosphere, the experience transitioning from immersive observation to memory and understanding that we carry back to our own world. The sapphire crystals still glitter in the metallic blue clouds. The heat still radiates from the layers below. The winds still blow at hypersonic speeds. The star still blazes in the permanently illuminated sky. HAT-P-7b continues as it was before we arrived in mind to observe it. The planet unchanged by our attention, yet now known and understood in ways it was not before humans developed the capability to detect and characterize worlds orbiting distant stars. The return journey across 1,000 light-years occurs instantaneously in thought, though the light-carrying information from HAT-P-7b still takes a millennium to make the trip. And we arrive back at Earth with knowledge of a place utterly unlike our home, yet operating according to the same physical laws that govern our own planet's atmosphere and weather. The comparison highlights Earth's hospitability, the narrow range of conditions that allow liquid water and moderate temperatures and breathable atmosphere, conditions that emerge not from universal planetary properties, but from the specific circumstances of our planet's formation and evolution. HAT-P-7b reminds us that most planets in the galaxy likely resemble it more than they resemble Earth, extreme in temperature or composition or atmospheric properties, challenging for life as we know it. Yet the knowledge that such worlds exist, that corundum clouds drift through alien skies, and gemstone rain falls on planets heated to temperatures that vaporize rock, adds richness to our understanding of the cosmos and wonder to our sense of what the universe contains. The science becomes poetry without ceasing to be science. The measurements and observations transforming into images of blue clouds, shimmering with crystal formations, of sapphire rain falling through superheated atmospheres, of a world so distant its light takes longer to reach us than our civilization has existed in its modern form. HAT-P-7b exists as both scientific data and as inspiration, both catalogue entry and as marvel. The quiet conclusion of our journey brings us to rest with fuller knowledge than we began. The exploration of HAT-P-7b, complete enough to provide satisfaction, while leaving room for future discoveries to add detail and nuance. The planet continues its endless orbit, completing another 2.2-day circuit around its star, the same face always toward the stellar fire, the clouds always forming and the rain always falling, the winds always blowing, the heat always radiating, the physics always operating according to laws we understand. The ongoing nature creates continuity between the planet we have explored and the planet that exists right now, this moment, 1,000 light years away. And so we leave the corundum clouds behind, returning to our own world with its water vapor clouds and liquid rain, its moderate temperatures and gentle winds, its solid surface and protective atmosphere, carrying memory of a place where corundum vaporizes in the heat and condenses into crystals that glitter in the starlight before falling and evaporating back into gas. HAT-P-7b remains real and distant, studied but not visited, understood but not experienced directly, known through the patient work of astronomy that extends human knowledge across the galaxy, one planet at a time. The gemstone rain continues its endless cycle. The weather proceeds according to atmospheric physics, and somewhere in that alien sky, corundum clouds drift through layers of superheated gas. Beautiful and extreme, impossible and real, a testament to the universe's capacity to create wonders from the basic ingredients of matter and energy and physical law beneath the glare of a white-hot star, on a world where it rains rubies and sapphires, where the impossible becomes everyday reality, where nature demonstrates that the cosmos contains variety beyond our ability to anticipate, but not beyond our ability to understand, through science that bridges the distances between worlds and brings knowledge of alien weather to minds evolved under Earth's gentle sky.